Okay, hi Sean, you can listen to us?
Yeah, do you hear me?
Yeah, perfect. Sorry for the delay.
I'm ready when you are.
We can start now. Okay, Monica.
Thank you. Okay, good morning, everybody. We are going to start the third day of the LatWaves. So now we are in the session wave forecasting, and the first talk is a keynote. He's remote. This is Sean Bidlot, and he's talking about the role of ocean waves in numerical weather prediction. Hi, Sean. You have 30 minutes for your talk, and okay, you can start.
Thank you.
Sorry, Sean, wait one more minute, because we are not looking for your presentation. But
okay.
Sorry,
you're not seeing my presentation?
Yes.
Yeah.
So
now it's
stop
okay.
Share and share again.
Oh, it's okay.
It is okay now?
Yeah, it's okay.
Okay. Yeah, I see now. Yeah, good morning, everyone. My name is Jean Bidlot, and I'm working at the ECMWF. This piece of work I'm about to present is in collaboration with Peter Janssen, who doesn't need an introduction, who is currently retired, but still very active and with me on the subject. And so the outline is a bit introduction of wave modeling at the ECMWF and why we do so. Then I will cover quite a large part of my talk on atmosphere wave interaction regarding the specification of the surface momentum flux, the surface stress, and a bit later on a bit newer pieces of work on atmosphere wave interaction regarding the control of heat and moisture exchange at the ocean surface, and then discuss briefly what type of other interaction I think we could be working on in the coming years. So ECMWF has been providing global wave forecasts for over 30 years now, since June 1992, and the quality has steadily improved, as shown by the left plot here. That is a RMS error of analysis in red and different forecast ranges over that period with respect to Northern Hemisphere buoys, and you see there's a slow decrease with time. Obviously, this is not to do entirely or if anything with the wave model. It's the global improvement of ECMWF forecasting system. But how can the wave continue to contribute to this progress? At ECMWF, we have a modeling configuration that is called the Earth System Model, which implies three main components: an atmospheric model, a wave model, and an ocean model. And in our system, the wave model is there to act as an agent between the atmosphere and the ocean, and by itself also do some interaction back to the atmosphere. The coupling to the ocean and the role of waves actually was presented at the last LatWaves. So for this talk, I will focus on the interaction of the waves with the atmosphere. So the main component is the atmosphere has to provide some wind. In our modeling configuration, we provide a neutral 10-meter wind. The wave model does this bit, and in return a Charnock coefficient, alpha here, that is used then to specify the surface roughness, so essentially the momentum exchange in the atmosphere. But the Charnock coefficient, without going into the details of the equation, is linked to the amount of momentum that is used to create the wave. So it's directly connected to the input source term. And based on this, you can have a Charnock that used to be a constant before this advent of coupling with the waves, that, as shown here in the plot, this is in terms of 10-meter wind, and you see there's about 1 order of magnitude in the value you can get. This is a density plot, so the red color indicates where you have most value, so roughly where the constant value would be. But still, under certain condition, there could be quite some deviation, and that this is the essence of the coupling we have at ECMWF. As a return, as a side for this, once you have this Charnock that depends on the sea state, then your drag coefficient depends on the sea state, and people quite often look at this drag in terms of 10-meter wind, and you see you have this cloud of points. Again, most points falls around this black line here. This black line is the same black line here on this plot that comes from this Edson and al. Paper, where they put together different field measurements and find this behavior of the drag coefficient in terms of the 10-meter neutral wind. And the ECMWF just fits perfectly with the data. This is to note between 0 and about 20 meters per second when most observations were available. In recent time, there's been some observation made under much stronger wind, under hurricane condition and all that. And we know by now that there's a tendency for the drag coefficient to tail, to come to a certain value and then start to decrease with high wind. And it is now accepted, for whatever different reason there may be, and it's open for discussions, for very large wind, the drag coefficient should attain a maximum and later on start decreasing. Based on this knowledge, we have revised our modeling over the coming years. And the two latest big changes we made, we moved to using Dragani et al. For the input and dissipation source term. So for most people who are familiar with this, is the ST4 in WaveWatch 3, but it's not exactly as implemented in WaveWatch 3. So in the ST4-like, this was implemented 3 years ago. And the latest one implemented over like 2 years ago is we realized that we need to do something to address this sharp decrease in the drag coefficient. And it was motivated for the last paper by Mark Donald based on his work, when he argues that, again, this is a drag coefficient in terms of 10-meter wind, that yes, you have an increase up to about 33 meters per second, and then a sharp decrease and a very strong wind, maybe a linear increase again. Based on this, we were forced to think, well, how can we do this in the modeling? And the first way we thought we could do this, it was a very simple way. We know that if we follow Peter Janssen's formulation, the Charnock coefficient is expressed as this ratio, where this tau W here is the wave-induced stress that is then divided by the total stress. U star cube is the total kinematic stress, and a coefficient here. This coefficient is a tuning coefficient, and then I'll come back to this. But in order to mimic this, we realized that this constant number up till now should actually become dependent on wind speed, and so we elected to make it, for whatever physical reason there might be, we said the Charnock somehow, the interaction with the surface has to start to be much less. So we implemented this where for wind above 33 meters per second, the constant we usually use is sharply decreased by about 1 order of magnitude. Based on this, we acquire a behavior of the drag coefficient as shown in here. Had we not done this change, we would have obtained a green curves here. So this is before the change in June 2020. These, by the way, are runs that we can these days run. We can run our system at 4-kilometer resolution. And if we apply the change, or if we use the default system, we get the blue curve, and you see the sharp reduction in the dry, and that has a marked impact. So this is Hurricane Laura from August 2020, when it was about to make a landfall on the Louisiana coast. And this is a 10-meter wind that I'm showing here. And you see the mark, very strong wind. The purplish color is about 70 meters per second. Had we not made this change, we would have obtained much lower winds. And therefore, we are in the process of testing our system at 4-kilometer resolution. And all my colleagues are very proud to see that our 4-kilometer resolution is really a step change in hurricane forecasting. Without this simple change, we would have had still very poor performance regarding our surface wind around hurricane. However, this solution didn't really satisfy me because it has no physics. It's a tuning exercise. You can see it that way. So Peter then got challenged into talking and realizing that maybe his model for wind wave interaction could be revised. And essentially, we revisited the problem, and we realized we had to introduce two new features in the model. One is the inclusion of a simplified model for the gravity capillary waves, so the very short waves that are not directly resolved by the model. As you know, we only resolve the large waves where most of the energy is. And also is the inclusion of a nonlinear effect on the growth rate. Essentially, it showed that as the sea state evolves, then the growth rate starts to have a nonlinear impact. Essentially, what it called a renormalization, it starts to be less because there's a nonlinear interaction. So to give you a bit of a flavor of what it is, in the original parameterization of the theory that Peter developed, always assumed that the wind profile will have to be logarithmic, as expressed here by this expression. And based on this, you come with balancing the different surface stress and the stress above. It comes with this formulation, essentially the Charnock relation. And you see, again, there's this wave-induced stress divided by the total stress. And you can either express this as a number, or you can also express it in this term when you have this Charnock-like constant, but with a small number, it's much smaller. And this is associated to represent the impact of what we couldn't represent at the time, the gravity capillary waves. So it was just, we don't know what it is, we're just going to represent it. And based on this, we then know that the theory comes with an expression of the growth rate here, the gamma, that once multiplied by the spectrum gives you the input source term. So based on this assumption, we realized that under very strong interaction between wind and waves, the wind profile actually should deviate from the log profile. And once you assume this and look at the stress balance across the wave boundary layer, you realize that the growth wave itself should depend on the spectrum in this form. So the growth curve that you should be using is the growth curve that you would be using if you had assumed that the logarithmic profile was still valid, time this renormalization, and N1, N2 are then a weighted integral of the linear growth curve by the spectrum, and N1 is weighted by the sine square of the direction with respect to the wind direction, the sine cube, and so N1 is always smaller than N2, and this term then is essentially always smaller than 1. And this is intended to replace what has been used as a tuning parameter in the ST4 formulation. Now, there's a sheltering effect, which is then represented by a sheltering coefficient, which is a bit of a big tuning knob. You say, how much should the waves shelter the other waves? But with this process, you actually bring a situation where the internal dynamic of the system does it. It's going to reduce the input of the wind input into the waves. And to give you a flavor of it, in here, this is the non-linear growth rate in function of wave numbers. It is bounded, as one should know. The dotted lines are what you will get if you had the linear system, sorry, the non-linear system, and the solid line is the linear system. And you see that for very large, this is by the way a simple one grid point simulation. For very large wind, like 50 meters per second, you see that indeed there's some quite large deviation with respect to what the linear growth rate would give us. So you get essentially less input. And for 15 meters per second, it's a lot less. So this tends to act mostly on high wind. The second aspect is you say, okay, we had hidden everything under this alpha B parameter that represent unresolved short gravity waves. And it was big on the tuning parameter that over the years we've been playing with it, but never really being satisfied with it. Then we realized that Peter had worked on this issue years ago by developing the so-called VIRS model, which was originally developed to try to represent a model, the radar backscatter, like for scatterometer data, among other things. So this model is still relatively simple, so we could implement it as a way to represent what the spectrum under these short gravity waves should be. And with that, then we will have to try to solve the balance that exists at the surface. So the total stress, the atmospheric stress, is the frictional stress, the wave-induced stress due to the low frequency, the part that is resolved by the wave model, and then the high frequency part, the one that contains these gravity capillary waves. But since both viscous stress and wave stress depend directly in a complicated manner on the stress itself, they all scale like the U star square usually. A stress balance has to be solved iteratively, so it's not an issue with a computer. And based on this, then now once you've solved this, you have a consistent solution for both the short and the long wave spectrum contained in the same time. Now, if you see what are the impact of this model on this alpha B, that you can say, well, you can try to see, and you see this is the different values with wave age. This is again a one grid point simulation, and you see for different winds. So the low winds are above from 5, 10, 15, and 20 meters, and you see that the default value you've been using is around between 10 and 15 meters, like the normal stormy condition, for which you will tend to turn, if you had to tune your model, that's where you will try to adapt. So you see that for high wind, it tends to be lower value, and for very low wind, it's high. And based on all this, you say, well, what type of drag coefficient do you obtain? Again, this is the same case. The blue here is the default operational model, and the red is what you obtain with these two features. So the nonlinear effect on the growth rate and this capillary gravity model for it. And you might say, well, it doesn't fit what you've had. Mind you that this blue is something I cooked up in a matter of a month. I say, well, what should we get so that we get roughly the right wind for the tropical cycle? The red is what you obtain with a model that contains some physics. However, since then, there's been a publication by Courage and House based on their simulation in the Miami wind tank, I believe, and in which they estimate, the drag coefficient and the very strong wind. They also found that some of the derivation of drag coefficient of early days of Mark, Dolan, and all were actually maybe slightly erroneous. So the study indicates that maybe the drag coefficient should be slightly larger. Now note that the x-axis is slightly different. It goes up to 80 here for the model, to 60. And so you focus on the red points, which are the new values from this paper. And you see that roughly it matches what the level of the drag that we get now in strong wind condition. And I believe that the tail here is roughly what you expect. There's still a bit of leeway where you say, we still lacked true many observations for extreme hurricane condition. Based on all this, how does it behave in the model? So to make it a bit interesting, I want to present this simple case I have here. This is a case that I was alerted about very strong wave hitting the coast of the state of Victoria in Australia, where boulders were projected onto the road. And here, if you see, what I'm showing is on the top is the wind speed, the significant wave height, and the equivalent significant wave height for long periods. And to the right is the difference between the new model and the old one. And what you see, there are some differences that start to appear in the wind. They accumulate in the wave field here, the significant wave height. At the bottom right here, it also accumulates in the low frequency part. We're talking waves between 21 and 25 seconds here. And as you go to a small animation, you see this signal propagates toward the coast. And by the time it hits the coast, you get these very large waves, as indicated by the few coastal measurements that we have for this case. Black is observation, blue is the old, red slightly larger than the blue is the new one. Here's roughly the place where these pictures came from. And you see, we're matching these very strong waves. So this impact on the wind comes back into the wave, tend to generate very large waves. Or you can see here's an histogram of the controlled, so the old system, and the new system of the 10-meter winds. And you see that for very large wind, the new systems tend to generate high wind, which I think is a good feature because people using ECMWF wind always complains that the high winds are too low. So I'm definitely trying to push for this system to become operational. With verification against buoy data, while you see a hint of improvement, we are in the process of trying to validate this against other data sources like SCAT data or SAR wind observation under hurricane wind, but I don't have a plot at this time. Now, you kind of always have to show that what you've shown doesn't degrade everything else. So if you go back to first observation, here is all wind observation in the northern hemisphere. The red is the new, and the blue, the control. This is a standard deviation of error. This is the mean bias, the bias. And it's here the standard deviation, the forecast, the level of activities. You see the red is slightly above. It means the system is a bit more active, which you expect to get slightly higher wind. The standard deviation is roughly in agreement, so it's deterioration. And similarly for the waves, you don't see much deterioration. So this is one of the main changes I want to put in. Now, for the remaining time, I want to cover another aspect. In a system like ECMWF, you have to model heat and moisture exchange, and usually you specify a heat exchange coefficient. By scaling, argument is proportional to the square root of the drag coefficient. So whatever you already have in the drag coefficient already influences the heat exchange. But then it's also proportional to the inverse of this log of 10 to ZT. ZT being is equivalent to the Z0, but for heat exchange. So it's the heat exchange roughness length exchange. And in our system, it is modeled as if there were actually no wave. If you have a flat plate and then viscosity is producing the exchange, and for that reason is proportional to the inverse of the friction velocity, with the nu being the viscosity itself time an adjustable parameters. But there's evidence that this heat exchange coefficient should actually have some variation with wind, and wind usually means waves. So there's a piece of work Peter did many years ago where he extended his theory to include wave effect. Essentially, you want to add the wave-induced motion in the lower part of the boundary area to actually contribute to enhancing the turbulent exchange. And once you put all this in theory, you come with a formulation that this roughness scale for heat exchange is enhanced for large friction velocity for large wind. The theory is many pages long, so I will not cover it, but the end result is you have this heat exchange coefficient in terms of the 10-meter wind. The blue one is what we have in the default system. The light blue one is what you get by just changing the drag coefficient. I said it was proportional to the square root of the drag coefficient. So if you change it, you change the heat exchange, which is something to remember, that heat and momentum exchange are often linked together in the parameterization. And with this new parameterization for direct sea-state impact on the heat exchange coefficient, you obtain the red. So there's an increase in heat exchange. As a consequence, you say, well, that has to be visible under hurricane forcing. I go back to this case of Hurricane Laura. This is the default system. This is what you will get with this change of the dry coefficient as I presented, but without the sea state and moisture added to it. If I add it to it, you see the wind, the hurricane deepens, and we run many other simulations, and you see it. You see a nice structure of the very strong wind band there. And so the validations that we've done indicates that indeed we are in the right direction. But it doesn't only have impact only where hurricanes are, because I mean it'd be nice, because they start acting every time you have wind. So this is again on the left here the heat exchange coefficient. The new one is the black, the green one is the old, and you see from as soon as the wind is above 15 meters per second, you start to have higher exchange. And as you would expect, this is a mean difference between new and old of temperature in terms of pressure. So it's essentially the vertical here, and it's a zonal mean. So from south to north, and you see the red indicates for both season JJA and DJF, and essentially the increase is happening in the winter hemisphere. So this is a southern hemisphere here, so JJA, and here DJF, and also in the tropics. Now, very convoluted plot, does it make any useful change to the forecast system? Here I'm showing a change in root mean square error when we compare the forecast with respect to the analysis versus, the T plus 12 hours, 1 day, 2 days, 3 days, etc. Blue means that there's a reduction, so it's an improvement. The hashing means that it's significant by the statistical test that our verification package is using. And so you see for both season tested, northern hemisphere summer and a northern hemisphere winter, there's improvement, most of everywhere. There's a bit of red, but that's to be expected. Now to finish, and I think it'd be a good thing to go back to Pedro's talk. He had mentioned, this wind, this 10-meter wind relative to the currents. In our system, in our coupled system, I've hinted that there's an ocean component. This ocean component gives information to the atmosphere in term of SST, as one will expect, but also in terms of currents. And these currents are actually used by the atmospheric system to compute the surface fluxes. Essentially, it means that you have to look at this relative wind with respect to the currents. However, if you look at what is happening into the formulation like Peter's formulation, you actually do the same calculation, because there's one thing to remember: ST4 or Peter Janssen ST3. The wind, it's not what the wind doesn't force the wave. What is forcing the wave is the surface stress in the form of the friction velocity. And internally, based on the update due to the sea state effect, you update this friction velocity. So in order to do so, you actually should also do the same calculation. You have to bring this calculation in, because it's still relative to this wind. And if you do so, because of a coupled system, the largest impact you find, yes, it's a bit on the waves. It's actually, if you remember one of my first slides, I say the wave also acts as an agent to transfer things like the momentum flux to the ocean. And then the impact then is felt at long time range, like seasonal time range, where the what I'm showing here is SST evolution for JJ and GJF with respect. So it's a difference here in the top right of each sub-panel, when we show that changing, going to a relative wind change essentially the surface stress, and in return, the ocean responds to change in surface stress in terms of change in SST, and it's much closer to what the observation is. So it's something also that to keep in mind. But to do it right, you kind of have to be in a fully coupled system, because the wind themselves will adjust to this presence of the surface wind. With this, you want to show that generally all these improvements are better. This is what we show to our management, is a so-called scorecard. It's very convoluted, but essentially all the columns which are red or blue, you want them blue as much as possible, because essentially this is different metrics of error, like from anomaly correlation to mean square error. Blue is an improvement. The top bit, you compare different variables that are shown here against own analysis, and the bottom bit is against observation. All my changes essentially are fairly neutral or improvement. There's a lot of blue, very little red. And against own analysis is also a lot. So this is reassuring. So we're hoping to push this for the contribution that will go not in the next model cycle, but the model cycle that will be used for ERA 6. And so I think it'll be very important for users to get all this right. Now, with the 2 minutes I probably have left, what else can we see? And I'm following a bit what Luigi was saying, that he believes the future is in air-sea interaction, and I couldn't agree more. So I say more air-sea, ocean, sea ice interaction. Eric had a great presentation on the nice work that has been done on adding waves into the sea ice and vice versa. We will follow this suit, because I think there's been so much work already. It's just a matter of deciding which one we want to put in our coupled system. We know by now, by also the nice plot that Luigi showed from Alex on the need to represent sea spray, because I believe, under very strong wind condition, the work I've described this doesn't really present sea spray, so we'll need to add some sea spray effect. We have also indication that, very small thing that's happening when waves are breaking, they generate bubbles, they expel, bubble exchange with the surface, enhance any form of exchanges, sea salt, aerosol production, gas exchange. I think as we move to fully coupled system, we need to start thinking about this. And also, a thing that I think is relatively simple to do, to start testing, the surface, it's not a flat surface. So when it comes to the albedo, so how much sunlight is reflected from the surface, there are two things that the waves are generating. They are roughening the surface, so it's not a smooth surface, and also waves are breaking. So these two can enhance or modify the albedo, so how much sunlight is reflected from the surface. With this, I hope I've given you useful information. I showed that waves are an active component of ECMWF Earth system. We use seastate information for momentum exchange. I've been doing it for years and can only recommend that people should follow this, because it's very, very useful. We are working to add these for other fluxes like heat and moisture, and in longer term, other fluxes, and continue this piece of work. With this, I hope I have time for 1 or 2 questions.
Thank you very much. Question, please. Okay.
Hey, John, this is Eric. Really nice presentation, and I can see a lot of useful stuff here. So 2 questions. One is your publication plans. Are you going to put this in a report or a paper? Because, like I said, it would be very useful.
Sorry, I didn't highlight it because it's small of a. It is already not internal, a tech memo that is available, but we are currently under review in JPO.
Okay.
Peter Janssen and myself.
Okay, great. That's fantastic. So, and of course, so in the Navy, at least in the global model, the atmospheric model, it's not getting feedback from the waves, and so. So we're not able to, we don't have this capability to use the physics parameterization like you have, but perhaps we can do some kind of dirty tuning to get roughly the same effect, at least in the short term, until we have the two-way feedback in place. And of course, for the regional model, we do have that feedback, so we can I hope you use that right away. So that's fantastic. Thank you, John.
Yeah, to answer thank you for your comment. This reduction of the drag for high wind is how I realized that other places, even if they didn't have wave model and a fancy coupling, had something that was a parametric or a very hard-coded limitation of the drag and reduction. Let it be, I think we got it from NCEP and the Navy, I think, and also the French, that they're all doing it.
All right. Thank you, John.
Hi, John. Luigi speaking now. And beautiful lecture, I can tell you. And I would like to listen again. I will ask you to pass me your lecture to learn more from what you have told too many things to digest in half an hour. Sorry?
Yeah, I hear you.
No, okay. No, but I'm very glad that first, okay, you listen to what I was saying yesterday. We had to be able to push on Earth interaction. The question is not to you, but is about the situation. How does the atmospheric community react to all this? Because I remember last time we were talking about this, you had improved the wave model, but this, I'm saying something wrong, but you understand what I mean. However, implementing this was deteriorating the rain in the equatorial zone or this sort of things, therefore it was not accepted. All these changes are in the right direction, of course, physical direction. Are they accepted, or how difficult it is to have the full community accepting this based on the official score of this sort of things? This is my question.
My recent experience have been that you really have to prove that you are making better scores, not just simple neutral scores, and they still have a view that, well, the Earth's surface is simple. There's so much more energy that's spent on the land surface, but it's 2/3 of the Earth's surface, so it still requires, and they still believe that whatever happened in mid-troposphere is more important. So it's very hard to make the case. It's a constant struggle because you still have this, oh, John, it's just a wave. And every time I show, the response of the waves usually affect the full of the troposphere. It doesn't go past the stratosphere because it'll be very hard for me to understand why. But it goes up to 200 hectopascals, so a few kilometers. And so it's just not just the surface.
No, that I was aware. That's the problem I heard each time was coming to ECMWF. That was a discussion. Right. Thank you.
Okay, the last question.
A more practical question, John. Thanks for the presentation. Very, very instructive. You mentioned briefly ERA 6, which for us, the community, we should be happy for that. There are new products coming along, but I'm also scared because we have just finished processing ERA interim. Now we are processing ERA 5, and now you produce something bigger and more monstrous. So could you give some quick details of what it is, the resolution, time lines, so on, quickly?
The timeline is to start sometime in 2024. So you still have a little time. The resolution is of the order of 18 kilometers for the atmosphere, and the waves will have the same resolution as the atmosphere. So also new features that I've not described, and hourly outputs, and it's big. The thing to connect here here is just, you know, Luigi mentioned, oh yeah, the ERA5 already have, you know, hourly global spectra, but it's way too much information. So we're planning to output many more variables regarding the spectral partitioning, so that you should be able to reconstruct the 2D spectrum much more easily. I mean, for your case, maybe the 2D spectra will still be useful, but it's indeed, it's a lot of data, but, you know, there's a need for it. Our operational system is shown to be quite superior to ERA5. So the community, you know, the meteorological community has made a lot of progress since ERA5. So that's why we want to do it again.
Okay, thank you.
Thank you.
Okay, we don't have more questions. So thank you very much.
Thank you.
Okay, now we can move to the next talk. We receive Leandro Farina, and he's talking about a deep learning approach for forecasting significant wave height. And we have in total 20 minutes with the time for question.
Okay, good morning. Thank you for the opportunity to speak again in this nice meeting. This time we're going to speak about forecasting of significant wave height using deep learning. One of the things I want to mention is that this work was funded by Office of Naval Research. So it's not written explicitly in the slides, but I just want to thank this and acknowledge this. This is a work done with my postdoc, Felipe Minuzzi. He could not be here at this time, so I'm presenting for him. And we've been doing this work in the last 2 years. The outline of the talk is like this. And one thing I'd like to also to mention is this is not, I'm not advocating anything in favor of using data-driven models against physical models necessarily. It's more like an experiment to show how far we can go and what can we achieve with this data-driven techniques. So it starts very simple. Now I think it's very understandable. I'm going to explain and what the first approach, and after that, I'm going to mention also a second approach that we implemented. This is ongoing work, and okay, let's see. I welcome any questions that you could have. So in introduction, I'll talk a little bit about what is artificial neural networks, the specific algorithm that we are employing in this case, which is LSTM, long short-term memory, which is very suitable for time series, especially for wave heights. So there are some very recent, I think there is a increase of works related to this problem in the last 2 years. And even 1.5 years, there are very important papers that were published on the LSTM for prediction of wave heights. Okay, so I describe here the first and second approach and some conclusions. So this is just to get an idea of where these methods are located. So we have this very broad area of artificial intelligence. Inside this, we have a subset of another method called machine learning. Okay, and a subset of machine learning is deep learning. Okay? So what are the main differences of these methods? Basically, machine learning doesn't necessarily use neural networks. Okay, so it's a wider concept, but it has some peculiarities. For example, in deep learning case, the computational demands are higher. Okay, so usually this term deep means we have a neural network with several layers, several hidden layers. So we have input layer, so you get where the data comes. So we can input the data, and an output layer where our results are obtained. And in the middle we have these hidden layers. Okay, so this term deep is basically comes from this aspect. Okay, so a basic deep learning is a deep artificial neural network. Okay, so basically we need one of the other things, more practical aspect. We need a GPU to run these models. Okay, it's not necessarily a CPU, and it has this. I think it's one of the main practical requirements of this. Okay, so just to put this very simple, in simple terms, I like to see this as if you think as a linear regression. So linear regression is a very simple technique that I think everyone uses. And we can start from this. Okay, so say we have these input values here, and we can assign some weights for these input values, and we can construct another function u. I don't know if you can read here, but basically u is a linear combination of the input with the weights. And then we can optimize this. Okay, so let's say the left-hand side is the truth, and then we can do this linear regression, and then we can get the output. Okay, so in the very simple form, I like to see artificial neural network as a simple case of linear regression. One difference here that makes a lot of difference actually is after you have this term here with this linear combination, we have this so-called activation function. Okay, this function phi or phi is a nonlinear function. Okay, so basically it looks like a step function. It can be differentiable or not, but this makes a lot of difference in the deep learning algorithm. Okay, so you get this combination of this linear combination, and you get the activation function, which makes this method nonlinear. Okay, so this is basically an artificial neural network. Here we have some other very common. I think all of you have seen this kind of graph already. So it's like a graphical representation of our neural network. So we have the input values here, the output, and we have these hidden layers. Okay, so the specific algorithm that we used is a so-called one of the recurrent neural network. Okay, so there are some connections in between the layers, so they can feed each other. Okay, so they can go back inside these layers inside each of these neurons. Okay, so there are some units called neurons. And when you have this recurrent neural network, this information can go back and circle inside each layer and neuron. Okay, so this is recurrent neural network, and specifically one of these subsets of these methods, recurrent neural networks, is this so-called long short-term memory. Okay. So what is going on when you have this recurrent neural network? You have to make this optimization in each layer, okay, using this gradient descent algorithm. And sometimes when you have this type of network, this gradient can vanish. So if the gradient vanishes, you cannot optimize your problem anymore. Okay, so you have this zero gradient, and you lose this strong component of network, which is the optimization in each inside layer, each hidden layer. So the LSTM prevents this phenomenon of happening. So you don't have this this gradient vanishing, okay? Because the information comes from all the layers, they are kept. Okay, So how they are kept? You have the so-called, for each neuron, you have a forget gate, output gate, and an input gate. Okay, so inside each neuron, you have these structures of gates, and this allows some of the information to go through the layers and or being forgot. All right, so in this way, you have the the system, the algorithm can remember some of the things which are very important in time series data. Okay, that's why it's so useful when you have this time series, specifically this one in oceanography with wave heights. Okay, I think I spoke about everything, all the essential things. Okay, so there are some equations that we could demonstrate this more clearly. In my case, because of my background in applied mathematics, I prefer to see this like a list of equations. For me, it's more clear. Okay, but usually it's representing these diagrams. Okay, so I think there are several ways of looking at this kind of networks. Okay, so what is the first approach? The first approach is very simple. Okay, but we try to make it simple, but also clear in order to interpret the results. We have played with two data sets. One of them is this high resolution simulations, and the other one with the real data, with buoy data. Okay, and then we made forecasts for 4 different lead times: 6, 12, 18, and 24. And okay, so I know ERA 5 is not a forecast. Our aim is to make a forecast, but it's very clear that ERA 5 is not forecast. But this is done just as an experiment, okay? Because for 2 reasons. ERA 5 is a reanalysis that has a very high resolution in space and time, so it's very complete set in contrast with a buoy data set or even satellite. And we can test the algorithm this way. But we are not, our objective is not comparing this forecast with data-driven models with ERA 5, because I know there are these 2 different objects. Okay, and the other reason is that because it could not get hold of forecast of waves for example, 1-2 years. So this is very difficult because some operational center, they have this information, sometimes they don't store this. Okay, because they are not interested in old forecast. Okay, so they make forecasts of last year. So who cares about this forecast anymore? But for research purpose, this is very important. Okay, so it could not get hold of this data yet, and that's why you used ERA 5. This is the other reason. Okay, so talking about the real data we got, we tried to explore all the data we have in Brazil coast. Okay, so this is more or less the situation. We have these buoys in deep water, okay, intermediate water and deep water. There are some other waves, some buoys in coastal water, but this is not interesting for us because we are comparing this with results that is not obtained for coastal waters and you know, all this transformation near the coast, and it's not our case. Okay, so what we have deep water, we have this set of buoys. This is provided by a program called PN Boya. Okay, so I think it's administered by the Brazil's Navy. Some of them are operational, some are not. Okay, here we have let's see the location of the buoys. Okay, starting from Rio Grande until Fortaleza in the north of Brazil. Here we have the water depth of each of these buoys located and a period of prediction that we use for our work. Okay, so this is the complete set we have. I think it's the most comprehensive one in Brazil. Okay, so this is an important experiment that we did. What is this? On the horizontal axis, we have all this time period of data for ERA 5, for example, not the buoy data, and we try to estimate the error. On the vertical axis, we have this MAP, so it's a mean absolute percentage error. Okay, so this is a measure of error against the training period. Okay, so say you have like 40 years of data to train your model. Okay, what we are going to use in order to make a wave forecast? We are not modeling climate. It's just forecast of waves. Okay, so we don't need probably we don't need 40 years. Okay, to predict forecast a very short range of wave height. Okay, so this is a measure of the error that we get. So in the horizontal axis we have this let's say 40 years, and the error, they go down after the first or the second year for each of the lead times per forecast. Okay, so in practice we don't need all this information before the second year. So roughly 1 year of training will be enough for this kind of forecast. Okay, this is what is showing this graph. Okay. Some technical information about this first approach. We use 80% of the data for training, okay, and 20% for validation. This is very standard. This was programmed in this Python language library, TensorFlow library, and this Keras APA. The method was concepted with mean absolute error as loss function. Okay, we have this loss function to optimize and to measure the error on each component and layer of the network. And this was optimized by gradient descent method, specifically Adam algorithm. Okay, so this is one of the main components of the method. And the architecture of the LSTM used is composed of 5 layers. Okay, so input layer, output layer, and 3 hidden layers with this number of neurons. Okay, so it's just more technical info. Okay, for the first approach, what is going on? We selected roughly 1 month, okay, to test 2019. And for example, for the lead time 6 hours, what we did was we saw all the data before 6 hours we performed the forecast. Okay, let's say we want the wave height is this time t0. Okay, so very naturally we collect all the data 6 hours before t0. Okay, and then here we stop. We don't see the data anymore, and we let the algorithm predict the wave height. Okay, and after this point we don't see anything, even wind. Okay, so there's no wind. The model just performs the prediction. Okay, for the next time, verification time, let's say T1, the same thing is done. Okay, so we advance a little bit with data. We can see more data and stop. And the idea is to keep this 6 hours window, okay, before we make the forecast, to characterize a 6-hour lead time. And the same thing are done for the other lead times with the same principle. Okay. So this is the machine we used. So this was obtained also with this ONR funding of the project. We acquired some of the specific machines for performing this. So we have an Intel Xeon processor with 20 CPUs, a RAM of 128 gigabytes, and a GPU, okay, to perform this. So some estimates of the time, computational time that we used. Okay, so we have for the, what happened? Okay. We spent 40 minutes for the training, for one whole training, and to make a single forecast, we used just a very small fraction of a second to make a forecast. So in computational time is much lower than a physical model, okay, to make a single forecast. This is the first result. In this case, we are comparing 3 things. You can see here. Let's see, you can point here. No. So the black curve is this LSTM prediction. The red one is ERA 5, and the other one is the buoy. Okay, so they are very similar for this lead time 6 hours, and the error start to increase naturally as we expected for longer, higher lead times. Okay, so this is result for Boia of Itajaí, the location. Okay, but again, we are using here compared with ERA 5. Okay, so the error is very small, so it's like 4 or 5%. Okay, for 6-hour forecast, and the error start to grow, as you can see here, where the lead times advances. Okay, so this is more like a academic experiment because ERA 5 is not a forecast. And next, what we did was we trained the model with data, with buoy data, all right? So we got some of these buoys, and we trained the model just with buoy data, okay, in these buoys of Brazil's coast. But the problem with that is that the data set is more sparse, okay, so you don't have all this rich information that you have in a higher resolution data set, okay. The error is higher, as you can see here, so you have 12% error of the machine learning algorithm. Against the buoy. So if we want to compare ERA 5, the buoy, you get a bit higher error, okay? And then you start to increase the error as the lead time goes, and also the difference between ERA 5 and the observational data also increase. But as you can see here, for 6-hour lead times is a very good result for the deep learning algorithm. Okay, so as we increase the lead time, not exactly. Okay, so this is the first result we get from the first approach. And what we are doing now is, that's what I call second approach. And this time we use actual forecast data. Okay, so we managed to collect 1 year of NOAA forecast for the points in Brazil that we are interested. Okay, Felipe started to save, every day the files, because I think the forecast data is available only 8 hours. Then they remove from the data. And then my postdoc, he collected this for 6 months. Okay, maybe now for these results, 4 months of 6 months. Now he has 1 year, and he's still working on that. And what is this second approach? The second approach, essentially, it takes into account the lead time. Okay, so each column of this matrix, this is the input data. Each column is related to 1 lead time. So we have different quality of data. Okay, so as you go to the right, the quality is deteriorating because the lead time is higher. Okay, and in the second matrix here, you have the target data set, which obtained from buoy, right? So basically what we are doing here, we are comparing the NOAA forecast with buoy data, and we are measuring the error between them, residual between them, and this is the object that we're going to train the model. The idea is to train the model to learn what is the residual between NOAA forecast and buoy data, all right? So this works much better. Okay, for this approach is very promising, but I can show you some preliminary results. And also the idea is to make this in ensemble mode, right? Because, this literature of deep learning method is increasing every day. So we have sometimes another algorithm that we could try. Why to stick with LSTM? We could try other things. And that's what we did here. Let's see if I missed one. No. Okay, so these are the first results. We used 4 months of training. Okay, and this is forecast, 6-day forecast. Okay, the location is Santos in the northeast of Brazil. There is a buoy there. And we have here the buoy data, which is this dotted line. Okay, and then this dashed line means the NOAA deterministic prediction forecast. Okay, so if we fix our attention in this line, this dot, not the dot, dashed line, okay, so NOAA forecast, as you can see, when we increase the forecast, it gets distant from the buoy data. Okay, so the error is higher, and this is very natural because this is a 6-day forecast. And the other curves is the ensemble, okay, of that we performed. Each of these lines is calculated with a different deep learning algorithm. Okay, so we have the algorithm here. We use LSTM, okay, on this part, LSTM, CNN, RNN, and other algorithms. I'm not going into details here, what are each of these algorithms. And have also a very important line in the middle here, which is the, okay, so it's not here, the ensemble mean. I'm going to show you the ensemble mean now. Okay, so this is a very typical spaghetti diagram of ensemble. 1 minute, okay. And then in this next plot, it's very much clear because I excluded all the ensemble members. So what we have here, the black one is the buoy data. The dashed one is NOAA forecast. And in the blue solid one is the ensemble mean. Okay, got with all these ensemble algorithms. So this looks like a very promising result because we can learn from the error between NOAA forecast and buoy data for this specific case. Okay, so it would obviously got closer to the buoy data than a typical physical forecast. So basically what we spoke here, forecast by LSTM, trained with high resolution simulation, and also with a sparse data set obtained from buoy. As we expected, the computational time is much lower than using physical model to make this forecast. And in the second approach, we use the actual forecast, not reanalysis data. For future research, what is possible to do, as we can see, one of the things is to make this forecast spatial temporal dependence, because as you notice, we perform a pointwise forecast for each point. So this forecast independent of the neighbors. So it will be very important to extend this to a two-dimensional domain, okay, to make a forecast of a region, not just of a point. Okay, so this is one of the most important things. How can we put physics inside the data-driven model? There are some options for that. For example, machine learning-based parameterization of small-scale phenomena. So this is done and taught in an atmospheric model. I'm not very sure about wave model, what we could do, because we could try to make some tuning or some of parameters in the wave model which are not, which has allowed this kind of tuning. I remember Alex mentioned that in ST6 this is fixed, so this is possibilities. Maybe it's not a case for one of the wave model, wave package, anyway. The other thing is to include physical equation constraints inside the algorithm. How can we do that? We can do this inside the loss function, okay, when we optimize the method, so we can force the data to obey a physical equation, so we can have a hybrid method. And this can be done also in the neural network architecture, so 2 ways. Another thing I'd like to mention is, which is being object of research recently, how to extrapolate regimes. Okay, so how could we make future climate simulations, projection, with this kind of data-driven models? So we don't see, we don't have data to see the future, and the challenge is how to train this in this situation. Okay, okay, that's about this. Thank you for the attention.
Okay, thank you very much. We have time for one question only. Oh.
Hello, Leandro. Thank you very much for the presentation. It was quite interesting, at least for me. I have one question, and it's about, based on your background, what you have done, do you think it's possible to predict, say, in a very short term, the profile of the wave or response. Say, I want to see how the surface elevation is going to be in the next 10 seconds, 15 seconds, based on time history of, I don't know, maybe simulating the wave spectrum by converting this into a time history of what happened in the past based on buoy measurements, for instance, because this can be very important for very critical, very difficult marine operations. You want to see what's going to happen in the next 15, 10 seconds. And if you can do something about this, you can increase safety. Yeah, that's my question.
Okay, thank you for your question. That's a very interesting point. I think some people in the University of Exeter in England, they are very concerned about this kind of forecast. We have this deterministic, very short range forecast for marine, maybe military operations. And I think it's quite possible to try something in this direction. We have what we did here, we just had used information from one point. So in this case, maybe we need more data set to train. But I think it's not a big step from what is done here.
Hello, nice presentation. I'm glad to see your work. I have some questions, but I'm going to be quick. The first one is, what will you do when ERAI won't be available? I mean, because artificial intelligence, like neural networks, needs a target. Yeah, so ANN mimics what would happen if you provide a target. But if it's not, how much time could you forecast? Is the first question. And the another question is, are you considering replace the input data with other physical parameter, maybe wind input or other parameter, to explain better what is happening with the forecasting?
Yeah, I'm not sure if I understood everything in your first question, but you mentioned the validity of the forecast, right? So with this kind of methods, and I'm also talking about the other papers that I read with the same approach, similar approach, the forecast is there is an improvement in the forecast for a very short range, let's say 6 hours. So far, this is, I think, what I saw, that you can have improvement from deep learning forecast of wave heights. And the second question, I don't know.
Yeah, if you are thinking to change the target.
Okay, more variables. Yeah, yeah. We tried this. I didn't mention here, but we tried to make the simulation with wind and wave period and some other variables, but we didn't have an actual improvement in the results. So all the results I showed here was training with only with a significant wave height. We try using another. In this architecture, we try to use another variables, but in this case, it didn't help. It doesn't mean that it's not useful and it cannot be used in other implementations. I think it's a very valuable information. For example, you can use the forecast wind to make this. So theoretically, it will improve, right, the forecast. So this is something that I think deserves more investigation. I think there are recent work published last year that what is done is an algorithm to try to learn the linear relationship between wind and wave height and wave. So this is another approach. Okay, so when you make the forecast, you use the actual wind and the actual forecast wind. We didn't do this. This was much simpler in the first approach.
Thank you.
Comments. effectively, these are probabilistic models, right, rather than deterministic for the wave forecast you are talking about, right? And it's interesting how they are coming back. A few years ago, we were writing a review paper, me, Eric, and a couple of other colleagues on wave current interactions. In the introduction, we wrote that the first wave forecast it was done by the Americans when they were landing troops in Morocco during World War II. And our anonymous reviewer came back and said, that's not true. The first wave forecast was done by French during World War I, and referred to some papers, 1918. We got them in French, right? So I had a student who translated them for me. And that was probabilistic forecast, right? Back then, obviously, there was no computers. There was no Hasselmann integral. Hasselmann was not even born, perhaps, right? And they looked at the maps of the pressure fields, right? And predicted what the swell would be also in Morocco. There's something about Morocco. It's coming back, right? I think Eric has a paper that the probabilistic forecast is more accurate at short time scales. That's the same conclusion that you made, right? And I wonder if, and then of course deterministic model, the conclusion was that the deterministic models are better, right? We're talking about short time scales like hours, then days, the deterministic models. And I'm just wondering that at even larger scale, right? Weeks, right? Not too many weeks, but 1 or 2 weeks, right? When we're basically talking about swell, which we don't predict well in the deterministic models, not only in terms of the wave height, but also arrival time. So we get everything wrong about swell, right? In deterministic models. Maybe the probabilistic models, again, at a very large scale, will prove more accurate, right? So maybe this symbiosis of these two can be useful, at least for practical applications.
Yeah.
Right. And what Juan said about very short, the question, right? A very short prediction, like next minute, right? I think here deterministic models should be used, right? Because this is still probability, right? Can be high probability, low, but not exact. But deterministic models at such short scales can be exact. If you look with radar, what is there, right? 3 kilometers away, then you're running very fast a phase resolving model, not spectral model, right? You can say what the waves will be right here in 1 minute.
Yes, just to comment, I think the most promising approach is to have this hybrid method that you can mix in a good way this data-driven model with this physical equation inside the same model. So this will be very interesting to see in the next years how it develops.
Okay, sorry we don't have more time for question. Maybe you can talk in the coffee. Thank you very much. So now we are going to now it's the time for Deanna Spindler from NOAA. She's talking about an overview of the NCEP operational wave models. Okay, we have in total 20 minutes, okay, but with a question also. So.
Good morning, everyone. I am Deanna Spindler, and I work at the Environmental Modeling Center, which is one of the operational centers that form part of NCEP. NCEP stands for the National Center for Environmental Prediction. It is a part of NOAA. So first of all, I would like to thank the sponsors, the organizers, and the helpers for making this meeting possible. It is always a pleasure to be part of LatWaves, and I love the enthusiasm in this group. When I was preparing this presentation, I realized that one of the goals of LatWaves is to increase international collaboration and to develop relationships between us. And this is one thing that we find now at NOAA. It really improves our science and our implementation. It simplifies implementation, and you will hear about this later in the talk. So in this talk, I have a lot of links to our products, whether they're operational, our websites, because I want to share this with you. And my hope is that you will click on some of these links and we can continue the conversation later. So I don't know if the slides will be shared, but if not, please just send me an email to deanna.spindler@noaa.gov. It's, wait, whoops, no. Okay. Well, it's right at the bottom of the first slide. Easy. And it will take me about a week to get back to you, but I will share the slides with you. So the content of my talk. First, I want to introduce you to the Environmental Modeling Center. It's also known as EMC, and what we do there. And EMC runs a lot of models, from atmospheric to aerosols, oceans, and I'm going to show you the operational wave models that we have. And then most of our wave models use WaveWatch 3, with the exception of one. So I will show you what are the latest developments we have in WaveWatch 3. And then I want to finish with what our developers have in mind for our next upgrades and the challenges that they're finding to do them in an operational center. A lot of this talk you will find it's the difference between a research center and an operations center. And I do this because as a student, I did not know what an operational center was. So this is mostly for the students. So at EMC, we run about 20 different operational models. And each one of these models was developed individually by different groups through different times using different ways. Now, when you have 3 models or 5 models, this might be sustainable. But when you come up to 20 models, this gets to be very complicated and it's unsustainable. So recently, within about the last 5 years, we have been tasked with simplifying this. So going from the left side, where you see how many different models we have, each little individual one, we're supposed to simplify it into what's known as the Unified Forecast System. The Unified Forecast System is also referred to as UFS, and it is basically an end-to-end numerical prediction system. What does this mean? From your data, your data simulation, prediction, post-processing, and verification, everything has the same workflow for each different model. It's also a coupled global system, so everything is together. And the other side of the UFS is what we do in LatWaves. We want to extend collaboration between the model developers, the research community, and then the final users, the weather prediction officers, or the weather forecasters. So the first implementation of the UFS that we did was the ensemble model. This is the Global Ensemble Forecast System, GAFS v12, of which the GEFS wave is just a component. So the GAFS has the atmosphere, the aerosol, and the wave model coupled. It runs on what was then the latest WaveWatch version, which was version 7, which right there is a huge upgrade, because the last ensemble wave model, I think, was version 3, maybe 4 at the most. So it's been many years. And that's one of the things that this unified forecast system is supposed to help us do, simplify the upgrade. So things improved. The models run 4 times a day. It used to go to 120 hours. It now goes out to 384-hour forecasts. It had 20 ensemble members. Now it's up to 30. The domain resolution went from 1/2 degree to 1/4 degree. And it's one-way coupled to the GAFS. So instead of getting the winds every 3 hours, now it gets the winds every hour. This, of course, led to a very nice improvement in the model results, and this upgrade was very happily accepted. The next upgrade we tried was for the deterministic model. And what you see here is just the significant wave height predicted for Hurricane Ian, which came into the Gulf of Mexico about a month ago now. I just wanted as an example of the GFS wave. But this implementation was a lot trickier than the previous one. The reason being is when you have many different little models, the way you run them, when you have a set number of resources, is if you remember the Tetris game, where you have the little columns of blocks that come down and you have to put them where the space is available. Think of the space available or your CPU and the computer time, and the little blocks with all the different shapes and amounts, those are your models. So you try to move them into place and get them to run all in what you have. When you have one unified model, you have a big chunk of space, but all the models have to run together at that same time. So we started developing this model. We thought we would change from our previous deterministic model was the multi-grid WaveWatch version. So multi-1, we had 9 nested grids with resolutions from 6 kilometers at the coast to 25 kilometers in the ocean. This changed. We thought, well, now we have more resources, we can do better. Between the 9 nested grids, there's a lot of exchange of information, which takes a lot of computational resources. So we thought we'd simplify the number of grids, simplify the number of interactions, and be able to get better results. The model was designed with 4 grids and did very well. But when it came time to implementation, we realized that we had about 1/3 less resources than they had promised us. Now, this was too late. The models were already coupled. The model has to be in the implementation, but you do not have the resources to run it as designed. So it was decided that one of the grids had to be sacrificed. And for all the students out there, I have 3 grids listed here, a 9-kilometer Arctic grid, 16-kilometer global grid, and 25-kilometer Southern Ocean grid. Which grid is missing? And I'll give you a hint. It's the one that takes the most resources. It's the high-resolution grid, our coastal high-resolution grid. We had to sacrifice it. And obviously, this degraded the results at the coast. This model is really good in the open ocean, but it's not as good as the multi-1 was at the coast. Now, when we presented these results, obviously our users were not thrilled with us, and they almost denied the implementation. So what did we do? We talked with them. We talked with the forecasters who use our model, and we found out what is most important to them. And it turns out what they really care about are when the waves are greater than at least 5 meters, preferably over 8 meters. That's what they call dangerous seas. And that's what they were looking at. Whereas if you look at the statistics of a global model, where I have data that I can compare, 95% of those points are under 3 meters. So I have very little data where they are most interested. So I had to look for specific cases and find the storms where I actually had data that I can compare to, and show them that GFS wave actually had better wind fields. That helped a lot because of the hourly wind forcing now. So we had the better winds. And the resolutions over the ocean part were definitely better. It was still not as good as multi-1 for the lower heights, but it did slightly better for these high waves. And that's what saved the implementation. Here I want to present, basically we're looking at Hurricane Ian again. And on the upper left is the 9 days forecast ahead of the storm. The dark line, the black line, is the buoy data. The little red dot, there, that's where the buoy is located off of the coast of Florida. And the blue line is the model result. So the top one is the significant wave height. Then we have the center graph is the wind speed, and the lower one is the peak periods. So the top left, you'll see that the dangerous seas were predicted 9 days ahead of the storm, which is pretty good. But the peaks are offset by quite a bit. by the time it gets to 7 days ahead in this top right, you see the peaks are starting to show up in the right place, and the height of the wave height is getting better. 2 days ahead, the peaks are lined up perfectly. This was also an improvement over Multi-1. Multi-1, the peaks of the storm were always shifted a little bit. GFS wave gets the peak better. And in the nowcast, you see the peaks are exactly ahead, and the model's actually underestimating a little bit. After overestimating for all the previous forecasts, it underestimates at the nowcast. But this is what saved the implementation, this kind of behavior. So this is one of our other operational models. These are coastal models. What that means, each of these little yellow dots is a separate model, a very high resolution local model that's built for that weather forecast office. It's run on demand. On demand means when they want results, they submit whichever winds they want to use to the AWIP system, and then the models are run at EMC and they get the results. This model was obviously developed before the unified forecast system, because our whole point now is to reduce the amount of models. This is 36 models right here. So this is going to be changing. It's also the only operational model we have that does not run WaveWatch 3. It runs SWAN. But eventually this is going to have to be upgraded into the unified forecast system, and at that point it will be switched to WaveWatch 3, and it will have different grids. The last of the operational models I want to talk about is the Great Lakes Wave Unstructured Model. Now, these Great Lakes are at the boundary of the US and Canada, and it's a self-contained model for the 5 Great Lakes. It runs using WaveWatch version 5.16, which already tells you the last implementation was in 2016. It's driven by whichever wind system the forecast decides, and it has a domain resolution at 2.5 kilometers. Now, right now, it's in the middle of an implementation upgrade. This means the developers have been writing code to try and improve the model. This will be the next version. Just last weekend, they froze that code, meaning they can make no more changes to the code. The version of code they handed in is what's going to be run for the parallel, and it'll be tested to see if it's better than this model. Now, what they did in the new implementation, or hopefully in the new upgrade, is they upgraded to the latest version of WaveWatch 3, of course, and they added Lake Champlain, which is a smaller lake here onto the right-hand side. They also changed the input ice field to a higher resolution ice field. Now, the Great Lakes was actually used as the V1 Great Lakes was used as a test bed for this unified forecast system. Why? WaveWatch 3 was already a community model. We already had established relationships with the researchers in the Great Lakes area, and we had very well relationships also with the weather forecasters of that area. So they were able to use this all together to smooth out the implementation. And that's one of the hopes of the UFS, is that we get to do this for every model implementation. And the paper up here on the right-hand side reports on how well that went. And to put it into perspective, when the deterministic multi-1 was implemented, it was a 7-year project to get that model into operations. For this Great Lakes model, it was 18 months. So that's the benefit of collaboration and open innovation between developers, researchers, and end users. So since the last LatWaves that I was here, I wanted to show what was new and what we have done in development for the WaveWatch 3. And the first thing is that the WaveWatch 3 code is now available on GitHub. So you can get it there. The next thing, for those of you who've installed WaveWatch 3 the old way, you know you had to use the .3 make and all the different functions. It's a lot easier now. Because of the unified forecast system, all the models have to be able to be installed with CMake. So WaveWatch 3 now has a CMake installer. Ali Abdullali has been working on a vegetation sync term. So that's also available. It's not run in our operational models, but it's there for research. And all of our tools that we've compiled over the years, mostly Python and shell scripts, are also available on GitHub. And these are tools that, to open and get the fields from the wave model, to plot the fields, to plot the spectra, they're all available. And finally, Ricardo Campos has released a 20-year wave reforecast, and this is available in here. What it is it's WaveWatch 3 forced by GEFS V12 winds. It's an ensemble. It runs once a day, has a quarter-degree resolution for spatial, every 3 hours temporal resolution. And it has 5 ensemble members. So you have your control member and then the 4 perturbations. And it runs once a week. It goes from 5 members to 11 members. Then generally it provides up to 16 days of forecast, and once a week that's extended to 35 days. All of that data is available, and Ricardo has a very nice write-up about what goes on, and it's available there. So what's next? These are our goals for the next couple of years. The first one is, same way as we have everything is unified forecast system. Now we have the unified verification system. The idea is that all models will be verified with the same functions. We want to improve that GFS waves so bad. We want to bring back the full capacity of the model. So we're looking at unstructured grids. Now, unstructured grids are wonderful because you can put the high resolution where you're most interested. They only have an itty-bitty little problem. These grids can be huge and grow to be monsters very easily, very resource intensive. So we're working on that scalability issue. And then the next versions are EFS, the ensemble model, and the deterministic model, GFS. Those are going to be two-way coupled. So first off, the EMC verification system, or EVS. This is being developed in the verification, post-processing, and product generation branch that I am a part of now. Basically, it wants to consolidate the verification to make sure everybody uses the same type of functions, the same definitions. Everything is specified out for all the models. So now, especially when you have a coupled model and you're looking at the verification of the atmospheric parts versus the verification of the ocean parts, it's all being verified the same way. It also removes the verification from the group that developed the model. In the old days, we had a wave group, and the wave group did everything, from input the data to the data simulation, to running the model, to producing the verification and showing the results. The same group did everything. Now that is split up across multiple groups. So the group doing the development of the model is separate from the group doing the verification. It's called independent, and they expect it to be better. It's all METPLUS based. So what is METPLUS? It's a C+ package that's already precompiled, and it's run with configuration files. It was developed for the atmospheric component over the last more than 5 years, and it's now at the point where it can be used for the other components. The code for the METPLUS is at the DT center here. And this other line where I say the code will eventually be available, that's the EVS code. So whatever code we use to verify our models will be available on GitHub. And then eventually we'll have a website to show the results of our verification. So these are the unstructured grids that we are looking at right now to bring the GFS wave back. And we have 2 ideas going right now. The first one on the left, if you remember the multi-1 grid, the multi-1 model with the 9 grids, you'll recognize those squares. Those are the original multi-1 grid resolutions. So what Ali took the unstructured grid and brought back the resolution of multi-1. On the right, he took the minimum between the multi-1 grid and the current GFS wave grid. So you can't see it too well, but these have very high resolutions around the US coast. Now the problem, of course, is the amount of nodes required for these grids. So the one on the left has 768,000 nodes. The one on the right, 1,814,000 nodes. These models, to run in the coupled system, you have 6 minutes per day of forecast. It has to run in that amount of time. So he's doing a lot of experimentation and seeing what he can do to get this to scale. Next is the two-way coupling. And you can see the GEFS, the ensemble model, will have the atmosphere, ocean, ice, waves, and aerosols two-way coupled. The mediator is just the one that takes the instantaneous time steps and averages them, or it also reconciles the grids between the models for each iteration. The models all are two-way coupled at each coupling time step. Now, you know everything I know about coupling models. So, thank you. Any questions? And I leave you with references. The top one is to our website where we have all the different models. You have to scroll down now to see all the different models. And the vegetation sync term, Ali has a very nice paper out. And then there's another paper on the unstructured development.
Thank you.
Okay. Congratulations for work and presentation. Excellent. And could you repeat or remind me, please, how many ensembles are you using with GFS Wave, please?
For GEFS, it's 30 ensemble members. 30 ensemble members. Okay.
Thank you, Deanna. That's a very nice presentation. So I've got two questions. So the first is about the prediction. You said the deterministic, the new system, it improved the prediction of the highest wave heights, which customers were interested in, like greater than 8 meters or something like that. Were you saying that that was because of the change in the wind resolution coming in, going from 3 hours to 1 hour, or was that just unrelated?
Well, we had the upgrade in the model, so the model physics were finely tuned. We also had the upgrade in the winds. I don't know what else was involved in it,
Right.
but the only other point we had was the higher resolution grids for like the global area. So that was higher resolution coming in, but we were missing the highest resolution grid, and that's what really.
Right. Yeah. So you don't know exactly what caused the improvement. And I think it's interesting because Jean earlier was talking about these highest winds and how ERA 5 gets criticized for that, and that he's got something to help with that. And you're pointing to something else apparently. So that could be an interesting discussion to have.
I think it's both ways because Jean also mentioned he had 4-kilometer resolution grids. So I'm jealous.
Okay, so my second question. So in your proposed unstructured grid, it looks like with South America, you've got there's this gradient. Right there. So it looks like you have a larger spacing in southern part of South America and finer spacing in the northern part of South America. So what's going on there?
That's because of the 3 grids from the GFS, so the deterministic model.
So you're following the previous thing.
Right. So he's using the GFS V16 grids plus the multi-one. So wherever's the minimum resolution is in this one.
It seems kind of, you don't need to do that, right? You could just make it a smooth resolution.
Well, yeah, depending on how many nodes you want to use. But what he's targeting is he knows we want to bring back those high resolution grids. But we don't want to give up now that we've seen how the 16-kilometer resolution grid, which is the center one, this blue one, that's 16 kilometers.
Right. Okay.
And we want to keep that because that does give nice results.
You don't want to lower the resolution, but you could raise the resolution in the other places, and I would expect no one would complain about that, right? But then you said you had the problem with too many nodes, so I understand.
That's the issue now.
Right. Okay. Thank you.
Yeah.
Okay, thank you.
I,
We don't have time, sorry. But maybe in the coffee, because we are very...
I have a question for Roberto. Is in the chat. I don't know. Because in the coffee he went.
Is here. Yeah?
Roberto, you can hear me? You can turn on your micro? The question is for the Wave Watch 3 global instructor, because of the very high resolution, hence small time steps, the implicit scheme will be used?
Actually, well, that's something Ali is considering, the implicit versus explicit. Basically, he's talking the card deck versus the global decomposition to parallelize the model. In the unstructured, it's going to be the global, what's it called? Global, it's not the card deck, it's the other one. So, but yeah, I think it's the implicit scheme that will be used, yeah.
Okay, thank you.
Okay.
Thank you. So the last speaker of this session is going to be Todd Spindler.
Good morning, everybody. My name is Todd Spindler. I work at the Ocean Prediction Center at the National Centers for Environmental Prediction. It's one of the 6 operational centers that were part of the original NCEP. And before I begin, I'd like to thank the sponsors and the organizers of this conference. This is the second one I've been to. I was in Medellin back in 2018. And I find this an absolutely fascinating place, filled with all sorts of wonderful synergies going on. And I hope to be able to come to the next one. The title of my talk is The Application of the Extreme Forecast Index and the Shift of Tails. The shift of tails at the Ocean Prediction Center for the forecasting of extreme wind and wave conditions. I'd like to talk, this is my outline. It's basically, I want to begin with an introduction to the Ocean Prediction Center, what we do and who we are. Then I want to discuss the project itself. I'll talk about the indexes, and I have 2 examples showing this, these new indexes to us anyway, in operation. Typhoon Merbok, which formed in September 14 of this year in the Western Pacific, moved north and became extratropical, moved into the Bering Sea. And the second one is the Southern Ocean in winter. I want to show where the indexes are useful and where they're not, and a little bit about why. And then I'll discuss a little bit about next steps on this project. First off, the Ocean Prediction Center is an operational center for ocean forecasting. As I mentioned, it was one of 6 centers that were originally created for NCEP. The OPC itself was originates and issued marine warnings and forecasts, continually monitors and analyzes maritime data, and provides guidance of marine atmospheric variables for purposes of protection of life and property safety at sea and enhancement of economic opportunity. These products fulfill U.S. responsibilities with the World Meteorological Organization and Safety of Life at Sea Convention, SOLAS. Now, you might not be familiar with SOLAS because it predates the World Meteorological Organization and the United Nations itself. It actually was an outgrowth, a direct outgrowth of the 1912 Titanic disaster, and was an international convention developed to help maritime safety. The Ocean Prediction Center has three main areas of responsibility. And you can see there in the upper left. The first one, I don't know if it's visible from where you sit, but these are the coastal zones. Now, they cover the exclusive economic zones in the east and west of the United States, which is basically, for us, where the Atlantic area and the Pacific areas, out to approximately 250 nautical miles. The second areas, there's two of them. There's the Med Area 4 and for the northern Atlantic. And on the west, we have Med Area 12. Now, these are part of the 21 zones that the World Meteorological Organization designates. We have a series of products that we produce on a daily basis. We have graphical products for the Atlantic and Pacific. We have text products which give warnings of wind, waves, visibility, icing conditions, and we have a series of gridded products that come out that are part of the National Digital Forecast Database. And we have a series of ice products that come out as well that cover the ice around the Alaska region, Great Lakes, and the Chesapeake and Delaware Bays. Now, just to give you an idea of how busy the place is, and it's not a very big place, there's about 35 people work there. Across the larger met areas, during the last 2020-2021 period, storm season, which, unlike the Hurricane Center storm season, our storm season runs year-round, we released over 13,000 warnings and watches for hazardous marine weather conditions, and tracked and forecasted over 100 extratropical storms. These services that we produce are in support of approximately $2 trillion of imports and exports being shipped into U.S. ports from 60,000 odd ships. And we deliver our information through various communication networks directly to the ships themselves, so the captains have time to be able to make decisions and move their ships, crews, and cargoes out of harm's way. Now, as I mentioned, there's a lot of storms in our area, severe storms frequently. And the question becomes, how can a forecaster in a short period of time determine whether or not these storms are unusual for that region? So, back in 2003 and 2006, the European Center for Medium Range Weather Forecasting produced two indexes, or published them, and which do exactly this sort of a thing. We have a very small development group. It's only about 4 of us. So we decided to take a look at this and produce a pilot program to see whether or not we could do it with the limited computational resources at our disposal. We do have larger computational resources for operational work, but as a development project, this was kind of off to the side. But the forecasters are very interested in these kinds of tools, something that can be added that will give them a quick decision-making process, whether or not this is a storm that needs to be paid attention to, or it's just, another day at the beach. So the big thing I wanted to mention there, of course, let's go back to that, is that we needed to do this with existing climatological data sets. There's a number of different data sets out there, and you'll see in a minute that we had to kind of build the stuff for ourselves as we went along. Okay, I want to begin with a quick depiction and run through on the ideas behind how these indexes work. So I have 2 diagrams here. They're idealized pictures of a climatology and an ensemble model. I should mention it's an ensemble climatology as well. That's important. On the left side, we have probability density functions, and we have the same data projected on the right side in the form of cumulative density. So the blue curves are the climate distributions. We have the climate distribution, and we have, for the same date and time, an ensemble distribution from the model forecast. You can see that the peaks are different, the mean values are different. The question to the forecasters is, are the peaks separated enough to call this unusual? So what you do is you take the data and you flip it into CDF format, which gives you a different set of the same curves here, or the same data, but the curves now are cleanly separated. And you'll notice in this condition, they join at the maximum value. And the ensemble distribution, ignore that little bit there, shows a clear distribution separation between the two sets. Now, just as a review, the PDF is, of course, the derivative of the CDF, and for the calculation of the index, I use the quantile function. You'll see why in a moment. Okay, the first index, called the extreme forecast index, looking from that same diagram I was just pointing to, you have the same curves. It's taken to a somewhat more extreme state here where there's even more separation. And for this particular case, it's an EFI calculation of about 80%, which indicates extreme conditions. If you're looking at the separation between the two, the overall question of determining whether or not the index is showing a unique, unusual, extreme situation is to calculate the area between the two curves. And the equation over here does just that. Yeah, here it is. And you calculate the area between the two curves, you know, in quantile formats, integrating overall quantiles over the range of 0 to 1. You divide it by a denominator, which is the square root of the climate quantile, multiplied by 1 minus the climate quantile, which basically acts as a weighting function to give you more emphasis on the tails of the distribution. And that's important because if you look up here at the blue section, that starts at the end of the extreme of the model climate and extends out to the end. Now, this area is where the really interesting stuff happens. But the problem is that the extreme forecast index only integrates up to the climate maximum. So in order to take advantage of the information in the further part of the distribution and determine whether or not this is an unusual event, you go to a second index. This is kind of a supplementary index. And in this case, same curve again, take into extremes, at least in terms of the ensemble forecast distribution. You have to look carefully at these two distances here, A and B. They're defined over here in the corner. What they are is from the maximum value, defined as the climate, and the 90th quantile, which is something of an arbitrary measurement, but it's standard between the ensemble forecast and the climate. You take the two distances between the 90th quantile of the forecast, the 99th quantile maximum value for the climate, and divide that by the distance between the climate's 90th and 99th quantiles, producing that simple index over here on the corner. Now, I should go back. I forgot to mention one important point here. That when you do this integral calculation on the extreme forecast index, it produces a number that is anywhere from -1 to +1. It's normalized, and if you have a value of 0, it's the model climate and the ensemble forecast are exactly the same. From the ECMWF recommendations, a value of the EFI between 0.5 and 0.8 is considered unusual. Anything above 0.8 is considered extreme. Here, this value is not normalized. It's non-dimensional, but it's not normalized. So it can occur with any value greater than 0. You don't worry about less than 0 values because in that case, the forecast is less than the climate. But according to ECMWF recommendations, a value of between 1 and 5 is considered unusual. Anything greater than 5 is considered extreme. So in order to calculate this, I needed a climatology. And unfortunately, at the time when I began working on this, over a year ago, we didn't have a good wave climatology, and we certainly didn't have an ensemble wave climatology. So what I did was work with existing data sets, 2 of them. The CFSR 30-year hindcast and the production hindcast. The production hindcast is kind of a funny one. We've been running it for a number of years. And that was simply a rerun of whatever the operational model was with the existing data sets to get a consistent set of data all the way through ran from about 2005 to 2019. I only wanted to look at the information to supplement what I had from the CFSR hindcast. So I took the information from 2010 to 2019, when fortunately both the operational model and the model that was used for the hindcast are roughly the same. So bolted them together, produced a climatology from that. Still didn't have an ensemble, so I had to synthesize one. I used a bootstrap resampling method, and that's a basic statistical resampling method where you're doing sampling with replacement from the data set to produce, in this case, an ensemble of 100 members. That number is kind of arbitrary, but I did that to try to improve the statistics. And once you have this, you don't have a true ensemble, you have a statistical ensemble member, which can be used for the statistical values, max, min, mean, and the quantile values I needed. And this is, I can go really quickly here because Deanna just talked about this. This is the existing operational YEF's wave system, 30-member ensemble, plus a control member, total of 31, if you include the nowcast, or the control member. Defined on a quarter-degree grid. The hindcasts were defined on the half-degree grid, which presented a small problem that I had to continuously interpolate back and forth between the grids and decide which way I wanted to settle on. For computational resource limitations, reasons, we decided to settle on the half-degree grid. Okay. Having gone past all that information, this is basically what I wanted to show, and I'm hoping this shows up okay from the distance. On the left side, we have the significant wave height, 48-hour forecast for Typhoon Merbok of the combined wind, waves, and swell. Oh, there it is. Wait. Okay. Okay, yeah, the title wrapped. Okay, here is Merbok here as an extratropical storm in the Bering Sea. The wave field here is extensive, and you can see heights here out to about 15 meters. The EFI calculation are the color contours over here. Now I'm projecting EFI values between 0.5 to 0.8 and above. That's your first look at how unusual the storm is. And the red areas in the center are the extreme sort areas according to the EFI calculation. On top of the color curves are the black lines. You can't see the dot. The black lines are the shift of tails calculations. Now the curves there are 0, 1, and 5. I wanted to see where it starts, and then at the point when it transitions to areas where, according to the shift of tails, it's extreme in the tails, not just in the bulk of the distribution. Now here you can see the history of Merbok as it moved north. And if you notice, when it goes north, now wait for it to come up. As it comes north, as it eventually comes north, there we go. The field is large according to the wind field and the calculations that we saw around that. It basically more or less fills the Bering Sea. The EFI indicates that areas well outside, what's going on? Well outside of the core of the storm are still showing high index values. Now it fills the entire Bering Sea and moves the points north of it. All that's indicating that the regions above the area and outside of the main core, the high energy core of the storm, are dangerous, or areas that are unusual effect. In this case, we know that because you can see the wind fields and wave fields extending far beyond where the core of the storm is. Now that's when you're working with a tropical cyclone and an extratropical cyclone. Here is an example from the Southern Ocean in winter. Same thing, significant wave height. But I want you to pay close attention to what's going on down here in the Southern Ocean. This was July 15 was the actual run. And there's some very large systems here moving, at this scale in particular, moving across the Southern Ocean. Large waves. 12, 13 meters. But you don't see anything going on here down in the south. Because according to the EFI calculation and the SOT calculation, nothing's going on there that's anything out of the ordinary. But at the same time, you see that there's an area up here in the central equatorial Pacific that is full of activity that's not reflected over in the wave field. And what's going on here is that because the wave field's generally so calm, anything out of the ordinary is kind of blown out of proportion by the indexes. So as far as the forecasters are concerned, you start with the EFI. You look at that to give yourself a quick snapshot of what seems to be the area's importance, but you'll have to go back to the main forecast. You have to go back to the main data and look at that and see whether or not what you're showing or what you're looking at is a genuine storm or just something that the EFI is not accurately projecting. So I realized when I put this together, I didn't put a conclusion slide in because this is not a concluded study. It's still ongoing. And what I have at the moment is a system that runs on a small system, small machines, limited resources, 4 times a day, producing information that we feed to an internal website for their forecasters to review. But the next steps are, when I had that synthetic climatology that I'm using now, I wanted to replace that with a genuine ensemble climatology so I can get the statistics better. So I'll be using that new GEFS reforecast. I'll be using the large member one every week, I suppose. And the nice thing about that is that they're both on the same grid. Because they're both on the same grid, I don't have to do the expensive interpolations, and we're looking at the process of moving it off the small system that I'm working on, the test system, up to our big operational supercomputer. And if that occurs, then we have the option of actually putting it into our production suite so that that becomes something the forecasters have available 4 times a day. Well, thank you. Any questions? I apologize, I can't read the references from here. But if these are put online, all these references refer to the EFI SOT publications, the Fort User's Guide, and the ECMWF tutorials and how to use the index, plus information on the Global Ensemble Forecast System and our ocean prediction system itself.
Okay, thank you, Todd. All the presentation are going to be shared as questions.
There's a question online, if I could ask.
Yeah, of course.
Do you hear me? Todd, do you hear me?
Yes, I can hear you. Who's talking, please?
It's Jean here. Very nice. Indeed, we have implemented this a while. Do you plan in your graphical display of these indexes to also include a panel that shows the climatology? I don't know if you've seen this in how ECMWF display these results.
Well, actually, that's already in place on our test website, which is internal only, unfortunately, and I can't show it here other than perhaps as an example. But yes, we do the climatology, we show the wave fields, and then we show the indexes side by side. And the climatology, we give all the basic parameters, the max, mean, and the min values for the forecasters to consider.
And is your climatology currently, or is in your plan, seasonal, meaning it's in the winter and the summer, it could be quite different?
It's actually calculated on a canonical monthly basis. And I use the months to interpolate to the day, so that I try to get the climatology as close to the.
Thank you.
More questions? So it's time for a coffee.
Okay, welcome everyone. Hello, we're starting with session 10 about wave climate and remote sensing. So the first speaker, the keynote speaker, is Jesús Portilla, and he will present characterization of the spatial structure of individual ocean wave field based on long-term wave spectra data.
Okay, thank you. Good morning, everyone. Thank you for attending this meeting. My name is Jesús Portilla from Escuela Politécnica Nacional. As you have seen, the title of my presentation has changed significantly, but actually the topic is the same. And the thing is that this subject was supposed to be presented a couple of years ago. And in the meantime, I managed to work it out because at that time was preliminary. I managed to work it out and also to write a paper. Now it's a paper under review in GJR. Probably one of the reviewers is here, and I still have a chance to convince that this is worth publishing. So for the benefit of compactness, the title is now The World Ocean Wave Fields. And as a subtitle, which is part of the title, I also acknowledge the source of data, which is ERA interim. You will have comments about that. We can talk about at the end of the session. So the purpose here is to identify, discern world ocean wave fields. And the motivation for this study is, and probably some people that have heard from me or have attended one of my previous presentations have realized that I always encourage people to work with the wave spectrum because in general, in the wave spectrum, there is a lot more information than what is in integral parameters. And I mean a lot more information. This example was shown by Christian a couple of days ago, yesterday, which is a very moderate example in which you have two completely or significantly different energy distributions, but you have very similar integral parameters. And that's the case always when you want to compare, you want to analyze data, you are not able to see all the energy distribution because you are only looking at one single parameter from a large matrix. So then when you start working with wave spectra, there is a problem because normally you can characterize easily time series like HS. You can say, okay, the wave climate is 5 meters, the period is 10 seconds or whatever. But then when you have long series of spectra, it's not that easy to characterize and to convey messages to the people about what it is in the wave spectrum. So for that, a few years ago, we developed a technique. Actually, we tried many techniques and we reported the one that provided the best results in order to make spectral statistics. And these are very useful because they allow you to see immediately some characteristics of the wave climate at any local condition. And plus that, you can get all kinds of parameters related to the wave spectrum. So first, we were using this like locally for some study cases, one single point, etc. But then the ERA interim was released in 2015. So I got very excited and I said we had already the methodology. This is only just a matter of putting the computer to run. And we, in that sense, we run and we process the whole ERA interim to obtain global spectral statistics. I will talk about this in more detail in one of the following slides. And this is a product that actually I want to show you and also encourage you to use, which is called GLOSWAC, was published also a couple of years ago, and in which we have all this kind of information. And actually, starting from this, you will see that it's immediate that you can connect some wave systems that are coherent in space, and it's like too tempting not to do it. So that's the present work, actually, the following of what was presented in GLOSWAC. So also in the course of showing this work to other people and also in the course of the revision process, I realized that I was using a terminology which is a wave field. But apparently my understanding of wave field was different than from the general public, and in general because the definition is too open. And I realized that when we talk about wave field, we actually talk about the sea state, what we see in the waves in the sea. But for instance, I have a couple of pictures here, and the acquainted eye, the experts, will immediately see here that there are many waves coming from different directions, and there are different periods, blah blah blah. So in general, what you see in the sea, it's not a single sea state, but actually it's a mixture of many waves that are coming from different directions. They have different periods, etc. And for an appetizer, I've shown some of the results here. For an example, like you have the North Atlantic, the coast of Spain, like you can have some waves that are generated by the northern trade winds blowing from northeast to southwest. And at the same time, you can have like storms blowing out from North America in the opposite direction. And at the end result is something like this. But the purpose for us is to be able to distinguish all these wave systems. So this is my methodology. I start with partitioning. That probably is very well known in this community. And then I will explain a little bit about the spectral statistics and glosswork. All these 3 points, they are not new. This is all material, this is published, but I will go briefly explaining this for the sake of completeness. And the other two steps, these are new. So through spectral correlations, we will see the equation is very simple. We managed to obtain coherent wave fields in the globe. So about partitioning, the concept is very simple. Actually, when you have some wind blowing over the sea, this wind will not generate a monochromatic wave, but immediately you will have a distribution. You will have many waves, different directions, different frequencies for the same wind, actually. And these appear like a cluster in the wave spectrum. So a cluster of energy beams, a cluster of energy, that is a wave system that belongs to one particular wind. And in general, if we see more than one cluster, that means that the wave conditions are bimodal, trimodal, multimodal. And that's what we see from general cases like ERA interim data, buoy data, basically all the data that we have processed. It's very rare to have one system in the sea. In general, you have many, at least 2. So it's important to identify them and to process them separately. And partitioning is simply the numerical algorithm that does this job. It's identifying these different clusters in the wave spectrum. So very simple. So then my point was like, again, you have all these time series of spectra. How do you understand, how you make sense of all this data? We tried several, along the years, we tried several parameters, like trying to get the average spectrum, these sort of things. But it's never satisfactory because everything is mirrored out. It's very difficult to distinguish one system from others, etc. So at the end, we came up with this methodology in which basically we process all the spectra from the time series. We obtain all the partitions, and each partition we represent only by a coordinate frequency direction coordinate. And so each partition will be represented only by one point. And these partitions will be represented in the same domain in the same spectral space. So we keep in the same dimensions of the spectrum, which is very useful. And so you have a collection of partitions that looks more or less like this, if you just plot dots. But this is a distribution. And if you put colors on that, if you make the distribution of that, you get something that is, strictly speaking, is the empirical distribution of partitions in the spectral domain. So this is not anymore a spectrum. Sometimes people confuse. This is not anymore a spectrum. This is this long-term distribution of partitions. But immediately you see that this is related to the wave climate. Because, for instance, these partitions at any particular location, for instance, here for an example, I took a point in the Colombian Pacific. You will not have, of course, you will not have partitions all over the spectrum. You will have partitions where they occur. And this is, of course, related to the wave climate. So, for instance, you will not have partitions somewhere here, because that would mean that you have swells coming from the continent, and that's impossible. So this is related to what is in the atmosphere. So this pattern became very useful at once, because in this pattern, actually in this distribution, you can see already different wave systems, and you can see some of the swells, very detailed swells that sometimes you, with the average spectrum and other parameters, you don't see. But in this distribution, there are more details appearing. So at the end, we kept this distribution as our main indicator for spectral statistics. So then the point is to, again, find the different clusters on this. And for that, you again apply partitioning. But now, and you obtain these different clusters. But now these clusters are what I call, and that's another definition, is what I call long-term spectral wave systems. Or in short, for friends, just wave systems. Yeah. So you can relate each of these wave systems to meteorological forcing. Like, for instance, in the Colombian Pacific, you can see this thing here more related to the trade winds from the south. You see this other component, which is related to the jets, to the wind jets in Central America, in this case, the Panama jet. And you can see also swells from the south, etc. You can start recognizing things in the spectrum which are related to the atmosphere. So that was published already, and then with this methodology that we had already, more or less at the same time, ERA Interim became available publicly, and then we process all the data, and that's also published, and it's available. The data is available in the website. So I really encourage you to use it. This is not advertising. Actually, this system, GLOSWAC, was sitting in my computer for a couple of years, almost. But the people who saw it, they say, why don't you share it? And I say, yeah, I'm happy to share it, but I don't have the means to share it. So then at the end, I made an effort to raise some money to pay someone to program this, because I'm not able to program web applications. And we put this in the web for the benefit of the community, because as I said, I had it in my computer already sitting for a long time. And then you have these spectral parameters to start with, and also other parameters that we compute. I'll let you check. But this is very useful, because if you click on any point, you can have at glance an idea of what is your local wave climate, not only in terms of a spectral distribution, but we also have integral parameters. So you can see what extremes you have, from where the waves are coming, which periods, which directions, etc. We have computed other parameters like wave age, thickness, wind. We have there also for interpretation. And basically the paper is kind of a manual of how you can use this data, how you can interpret, and that's basically what the paper is. Okay, so that was our starting point. And the thing is that, to give you an example, I choose one point in the region, because we are here in the South Atlantic, so I choose one point here, or several points, 4 points in this case. So you click on one of the points and you get what is the long-term spectral distribution of this point. And you can see, for instance, here in the South, some of the presentations before have shown that this is a very stormy area, as it is indeed. You can see that the spectral distribution is a mess. You have wave systems all around the circle of the spectrum, because there is a lot of cyclogenesis in this area. There are a lot of storms passing by, always rotating and generating all these kind of waves. And then as you go a little bit more to the north, the situation is more calm, and then there are less wave systems. And mainly what you can see here is two longshore swells. With Nelson, we have been working with these longshore swells. And another offshore wind sea component. And the further you go, like in this third point, we are in front of Uruguay. One of the systems has disappeared, but along the two longshore swells, they are still there. And then you go a bit northern to Brazil, and then you still see these swells, plus another wind sea recurrent in this area. So that was our starting point, because if you pay attention, for instance, to this system here, and you go point by point, and you locate it in the other points, you see it. So you see it here, you see it there, you see it there, and everywhere around in the area, you see it. And all these point systems, actually they are related. They are related in space. They are the same. So the challenge, or the simple point, was then to try to connect all these systems to have a consistent wave field in space. That was the main point. And for that, we tried several methodologies, including clustering techniques. We work with Francesco and Ismar, also working with self-organizing maps. We have applied some of his clustering techniques. But I can say that if you want to try something like this, I can say that all of them, they have some skill. All of them, they show what the wave field should be, but with limitations. So at the end, we ended up with these correlations, which are spectral correlations, and they became much more robust in identifying the structure, the spatial structure of these wave systems. And I will try to explain how these correlations are obtained. If I don't succeed, please let me know. So what we do is, at one specific point, like in this case, this point is in the equatorial Pacific, we take one wave system of this, and we calculate the correlation of this wave system with all wave systems of all the points in the grid. And so this correlation involves frequency, time, direction, but also time, because this is a long-term wave system, but actually this represents a time series of partitions in the whole ERAI interim. So there is a huge amount of data. So this parameter is robust, because the amount of data is huge. So when you make these correlations, some patterns start to appear quickly here. And for instance, the system we were looking before, this pointer is very tricky. So it's this one. And this represents actually the swells from Antarctica. And these swells from Antarctica, actually, they are huge wave field that covers almost the whole globe. It is represented here. So you see that these waves from Antarctica, these storms are circulating freely around Antarctica, and they are producing these swells, and they are radiating these swells all over the world. And actually, somehow the same swells that you have here in Uruguay, we have also a component of that in Ecuador. So we share these swells from the Antarctica somehow. So they cover basically the whole Earth. The other one is this one, coming from northwest, which represents the northern storms. It's something similar. The North Sea, the North Hemisphere has a lot of activity also in the winter, and all these storms also produce a lot of swells, and they radiate all these swells all over the Pacific in this case. And then we have other systems like this one, which Paco will recognize immediately. This is related to in this case, this is very related to the jets in Tehuantepec. But not only that, these jets are also related to the northern trade winds. And you see immediately the patterns here. And these other ones, I will concentrate on this for an illustrative example here. These are the southern trade winds. So I will be talking more about this wave system for illustration. So this is the kind of pictures that you can obtain from this correlation. A very nice, homogeneous, consistent wave field. But if life were nice and pink and everything was perfect, that would be the end of the story. But unfortunately not, because as probably you have seen already, like there are still positive correlations with this point. So if we claim that these are related all to the southern swells, there is something wrong here, because, for instance, you have positive correlations also in the Caribbean and also in some other areas where there's no possibility for the swells to get there. So the thing is that apart from the wave fields, these correlations are identifying teleconnections. And that's interesting by itself, but for the purpose of, for my present purpose of determining wave fields, it's inconvenient. But on the other hand, we have another way of detecting these teleconnections. And at the end, I will talk a little bit about these teleconnections. So the way to correct this, the way we found is that in principle, yes, these correlations are able to detect the wave field, but somehow we have to cut all these teleconnections. And the way we did it is to truncate this correlation map, the area of the correlation, at any threshold you want. The thing is that the bigger the threshold, the smaller the area, and then you need more points to calculate. And these computations are expensive, so I have to somehow balance how many points and how much precision do I want compared to computer time. So if you cut the correlations of one of these swell systems, then you get rid of the teleconnections. But then the problem is that you have to put again everything together. So we calculate this for several points, as many as possible, as computer allows. And then you get rid of the teleconnections, and then you put the sub fields back together. That's what is represented here. So let's see some results. I have a picture here of the average global wave height, which might be very familiar to you. It's very common in textbooks and everything. So things that we know, there are big storms, big waves in the Southern Ocean, of course, the biggest. There are also big waves in the Northern Hemisphere, Pacific and Atlantic. And in the equatorial zone, apparently not much activity, boring, apparently. So we start processing this. And now that we have separated and we have identified the southern swells, so we can compute it, we can extract it, and we can extract it from the total. And one of the ones that I wanted to extract were precisely these two, which are very, very energetic. The magnitude is very large. So this one is the southern swells, and this is the northern swells. And then in the next slides, I show how these wave fields are extracted like onion layers from the total data. So we have the total here. And if we extract from the total the southern swells, we end up with an image that is like this. And then from this, we extract further the northern storms from the Pacific. And then we end up with an image like this. And here you start seeing other things. And for the benefit of contrast, I changed the color scale. These two are the same, but this is with a different color scale. And then you can start seeing like northern trade winds. You start seeing the southern trade winds. You see some jets, many features. And so the processing is just remove one layer at a time to separate everything what it's inside. So for this presentation, I've concentrated on the southern trade winds because of personal interest, because also they are global. They are in all the oceans. So the other reason is that these southern trade winds, they are in a layer which is below the very energetic ones, so it's nicer to see them. And this is an example of what you can calculate once you have separated this specific wave field. So, for instance, you can calculate the magnitude of this wave field only. Here in the other map, I show the directions. Like you see, there is a core direction in all the oceans, more or less at minus 60 degrees. And if you go to the right of the core, the directions are more north. And if you go to the left of the core, the directions are more to the west. But we have the time series of the whole time series of this wave field. So my argument is that basically this consists of another data set, because you can analyze this separately, especially for climate. It's very useful because you can check what has been going on only to this wave system or wind system alone. And you can analyze trends. You can analyze the connection between one wave system or another one. And another point is that for analyzing this kind of climate patterns, waves are much more, I messed up? Yeah, no, okay. Waves are much more useful because the signal, it's much more stable. Because if you try to analyze the trade winds, looking at the winds only, these winds change in a matter of hours, and they overimpose. You will not see immediately the northern trade winds, the southern. But in the wave signal, because the waves are integrated, it's an integrated effect, the signal lasts longer, and also it occupies a longer space because these waves will continue to propagate, and you can see the effect of this meteorological forcing in the basins. So another thing that you can do for climate, I concentrated here in climate, but there can be other applications. I see immediately also another application in data assimilation. For instance, you can obtain monthly distributions to see how this changes in seasons. And like we see here, for instance, in July, June, July, August, this system is the strongest. And it is the weakest in January, of course, we know that. But in this case, if we can analyze by month, by year, we can check for any anomaly or whatever the case might be. And especially these trade winds are important because they are always associated to dry conditions in land. For instance, the coast of Chile, Peru, they are affected very much by the trade winds, and it's a dry zone. The same is the case in Australia and also in Brazil. I've read in the meantime that, for instance, in the north part of Brazil, there can be droughts that are associated to this component in relationship to other indexes like ENSO and these sort of things. So this is the kind of analysis that you can do. I haven't done it very deeply, but the thing is that I will be very happy to share this data. So if anyone wants to work in one of these systems, analyze climate or whatever, just let me know. We can interchange data. You can apply it in your region. So you can also look at trends because well, here in the previous slide I only show the average of the seasons, but also for instance, I want to see what it has been going on along the years and along the months with one specific wave system. In this case, we are still talking about the southern trade winds. And the first picture above is familiar to us already because we have been working already in this area, is the behavior of this wave system in one specific point, which is in the Colombian Pacific that I showed before. And then what you can see here is that there is a nice modulation due to the seasons, like the peaks are July and troughs are January. So you see that this thing follows very nicely the seasons. And then you see these very conspicuous lows. And actually that was very interesting for us because we are from the region there. We know it, and these two lows correspond to very strong ENSO event. So somehow these ENSO events, they are appearing here also in the wave sign of the trade winds. And then the conclusion, the fake conclusion, I would say, is that we think that during the ENSO years, the trade winds go down. But actually, when we check the whole field, it's actually not the case. Actually, during the ENSO years, this system goes stronger. So there was an apparent contradiction in that. So we tried to analyze a bit further to see, because apparently it's not the intensity of the trade wind which is changing. It's the distribution of this system over the space. So we wanted to check that. And for that, we computed these other two parameters, which is the latitude, the average latitude and longitude of the core. And the core means the points which have a wave height larger than 1 meter. So in that sense, we can compute how the core, the biggest part of this wave system, has been moving around the Pacific. And we see again, for the latitude, again, a nice modulation that we know also because we know that the trade winds are related to the intertropical convergence zone. And this intertropical convergence zone is, of course, moving up and down with the seasons. So we see again this signal here. And for the longitude, this modulation is less clear, but still you see some trends, you see some patterns. And for instance, for the same years that I was mentioning before, the trend in the latitude and longitude is in general that this core has gone too much to the south and also too much to the east. So it has moved to the south and to the east. But apart of that, so you can see other things. I haven't analyzed everything here. Something that calls my attention is these peaks in 1993. Like this system has gone very, very far south and very, very far east. But actually, this is not an ENSO year. So there are many things to be checked there. And also in the longitude, there was another interesting thing to see, and is the periodicity of the ENSO, like ENSO kind of signature on this. And it's like before, people used to talk about the ENSO recurrence of about 4 years. And actually you see something like 4 years recurrence on this up to this point. Up to this point, you see more or less something like a recurrence of 4 years. But then this recurrence has disappeared. And actually that's also interesting because after the event, the ENSO event of 1997, we haven't had a real ENSO that you can call ENSO. So somehow this is also appearing in this sign. So this is only an example. We didn't mean to analyze everything of the trade winds of any particular wave system in particular. This was more to illustrate the methodology, how to use it, which kind of parameters you can obtain from that. And as I said before, if someone wants to work in some of these things in her own area, I will be happy to share the data. So coming back to the correlations and the teleconnections, then we realize also that we have a byproduct, which is the teleconnections. And I show here a couple of examples related to the Indian monsoons. Like if you have the point somewhere in the Indian Ocean where the Indian monsoons appears, the left is the winter monsoon and the right is the summer monsoon. So one of the things we see is that this system actually is not completely correlated to the northern trade winds. It is something different. It's another mode. And the interesting thing here was to see that this system has some correlations here in front of Mexico, like in the jets in Central America. There are also correlations here in Africa and also some others in Brazil. Who knows what they are? Interesting to analyze. And the other system was also interesting for me because this is the summer monsoon. So you have winds blowing from Somalia towards the east, and you see that there are some components also here in front of the Philippine Islands. And also an interesting thing of this system is that it is very tropical. It's very locally tropical, and because here, apart that these correlations always tend to produce positive correlations, here like you have zero correlation of this system in the tropics. But for instance, you have all these other components, and this has intrigued me always because we always in the signal, also in the buoy signal, we get some waves coming from west that actually we didn't know what they were, and actually they seem to be related to this monsoon. And well, you see another component also in the other extreme in Africa. And apart from that, you have some correlations with the southern ocean and around the Antarctic. So another thing to analyze, like for climate, that will be very interesting. This thing, and another thing that was probably more related, but one of the reviewers asked me to put this. First, at the beginning, I thought this is nonsense because I'm working with model data, but they wanted to see what this compares to observations, but that was more related to the paper of 2015 that we also already did this kind of exercise. In any case, I did it, and I'm happy because the results were interesting as well. So we took 3 buoys, one buoy in Hawaii, the other buoy in front of Peru, and the other buoy, the Brazilian buoy, here in front of, this is Rio Grande, right, Nelson? And we compared the signals, and we saw that whenever we compared the signal of the buoy and the model data, the long-term signals, they are very consistent. Like for instance, you have these systems here, and they will appear here with another characteristic, of course, because the sources of data are different, the resolution is different, and you have another system here that will appear here as well. This is the Hawaii buoy, and this is a very challenging buoy because you are in the middle of the Pacific with a lot of swells, very difficult to model. So I don't claim that the magnitude should be okay, but at least the spectral pattern is very good for a Central Pacific buoy, and the same for the Brazilian buoy. So we have these 2 longshore components that they appear also in the buoy data. There is another one here. There is another system here that it does not appear in the model data. But then we were not worried at all, because if you go a little bit in another point, not exactly the same point as the buoy, but you move a little bit offshore, and then you find this. So it's a kind of representation problem of the model, but this system exists. So it's a kind of a verification of both sources, I would say. And this for the Peruvian buoy, something similar. We have the southern swells here. We have the northern swell storms here that they appear with some other signals, and the trade wind signal here. Some other signals there. But then what we realized also is that because normally we process and we use the data from NOAA, and we process the buoy data with their methods, this is Kaik et al. And actually the results were not very good. I was not very happy with many buoys of signal of the NOAA using the Kaik 2D distribution. And that is what I was mentioning to Diana. So for other buoys, somehow some other manufacturers, they are using the maximum entropy method for processing the 2D distribution of the spectrum. And actually, this distribution obtained with the maximum entropy is always more consistent than the Kaik distribution. So more and more in time, I'm more inclined to use the maximum entropy than the Kaik, and also thanks to Eric that passed me the code to compute all these things. It's part of this processing. So yeah, at the end, I hope the reviewer will be happy with this. I'm happy anyway. So we managed to make some comparison at the level of spectrum. Some other pictures. I have time or not? I will go very quickly. This is the kind of examples, because you calculate correlations in many points, and you have very nice signals. I wanted to show some examples here, like for instance, in this for this point in the Antarctic, you get the signal of the Californian jet, very nicely shown here. There are other things like this was interesting also, because apparently the southern trade winds, they have also like a different modes. There are relationships like between the California jet and the Agulhas jet. There is another thing here in Africa, and many things like this. You see plenty of pictures and you see plenty of patterns, which look very interesting. So And yeah, for conclusions, if I have time, otherwise I let you make your own conclusions, and I preferably leave some time for questions if I'm running out of time.
Thank you, Jesus. Very nice talk. I like it really much. And I tend to think, especially we do measurements in the field, I tend to think that the waves can be considered as random, right? Random processes. And yeah, most of us consider that. And then the natural character of the wave field, of the wave systems, is they have intrinsically variability, and we can say natural variability. So the basis of your work is the partition in the spectrum, right? That's fine. My question is, have you thought about including something, I don't know what, in your results or in your analysis to incorporate this kind of natural variability of the waves?
Somehow, well, in our model, our model is stochastic in nature, but we have some kind of deterministic response or output. And for instance, in this case, if you look at one wave field, let's take this as an example. This is an average. So this is obtained, the whole picture is obtained through statistics. But of course there will be variability here. So sometimes it is possible that some of the points, many of the points will not have any significant wave height in that sense. So this is not strictly related to what you say, but there will be variations. So sometimes if you plot the time series of this wave field, it will go very down, it will be 0 sometimes in some regions and blah, blah, blah. But that's what the model contains. The thing here is that statistically, we have determined the domain of this system. The variability, the natural variability should be in the observations. So in principle, we don't have this in the model.
Yeah, but the point is how to incorporate in your analysis and results. For instance, for one particular wave system, though generated by storms in the Southern Ocean, for instance, it's fine. You have the plot and the correlations and all that, but those must have some variability, natural variability in reality, right? So the question is how to include or incorporate that, but that's all right.
So very much in detail, I haven't thought of that, but as I said before, for instance, the storms will pass, and some storms will, I don't know, generate more waves towards the Peruvian coast sometimes. Another storm will generate other swells that are more directed to the Colombia or the Central America and things like this. So this variability, because it is in the model, will be there. But real natural variability, like all the details of the wave field, no, not yet. But yeah.
Thank you.
Okay, last question.
Thank you, Jesus. That was really good. So on this, the thing that really caught my eye here is the teleconnections and using correlations. So just, I'd like you to clarify what you're trying to say about the, so if you have, let's say you have a wind system that's partially in one ocean and partially in another ocean and sending waves out on each, are you calling that a teleconnection or something else?
No. For instance, if you talk about the swells in the Antarctica, they are not really teleconnections.
Right.
Because this is part of the swells, the storms that are passing by, and they are radiating swells. These are not teleconnections.
Right.
The same for the storms and the same for the trade winds, for instance. Because the trade winds, they have a component in each of the oceans.
Right.
So you have 3, and actually you have 4, because apparently there is another component in the Central Pacific, because the Pacific is so huge that you have another component that is not very well defined, but it's there. And this is related to, because of the characteristics of the spectral signature, they are related to this meteorological system.
Right.
And you see consistency in time, you see consistency, you see consistency in many.
So the fact that you see unexpected correlations between 2 oceans doesn't necessarily mean a teleconnection. It could, but not necessarily.
Yeah,
right.
It could. For instance, in this picture, like, oops, I'm going back. In this picture, okay, I'm trying to see what's the wave field of the winter monsoon, and then I get high correlations in Central America. I think somehow these are related to the same meteorological forcing, right, but they are not directly connected. Like, for instance, this thing in the Indian Ocean, and also here in Africa. They are not directly connected.
Okay.
These are not the same waves
Right.
going from one place to the other.
It's not the same wind system.
No, it's another thing.
They're connected.
So they
Okay.
are related.
Yeah. Okay.
I don't know how, but they are
Okay.
connected.
All right. Thank you.
Okay, thank you, Jesus. We welcome the next speaker, Walter Dragani from Argentina. And the presentation is about detection of pure swell in the Outer Río de la Plata, Argentina.
Thank you very much. The title of the presentation is Detection of Pure Swell in the Outer Río de la Plata, Argentina, between Argentina and Uruguay. And this presentation was carried out with the collaboration of Alejandro Salimbeni, Guadalupe Alonso, and Yael Perez from the Navy Hydrographic Service and the Buenos Aires University. First of all, I would like to explain what is pure swell for us. There are 2 things to say. First of all, they are propagating in a direction practically contrary to the local wind. And secondly, they are present without significant sea. Then pure swell could be understood as dominant swell as synonyms. 2 words about the Rio de la Plata story. It was explained by Rodrigo Alonso yesterday. It is divided in 3 main zones: the upper, the intermediate, and the outer zones. The first one, upper and intermediate, is predominantly a fluvial zone where the Rio Paraná, Uruguay rivers dominate the zone. And the other Rio de la Plata is a more oceanic environmental, where waves, sea, swell, longshore current, breakwaters, breaking waves are present in the zone of the Outer Rio de la Plata. Some specific antecedents of this issue. There is a very few antecedents in the peer review literature. Perhaps the first one is due to Anschutz in 2000 in a congress in Madrid. He said that waves are a combination of sea with periods around 4 to 6 seconds and swell with peak periods around 10 to 12 seconds. Subsequently, we published that sea height is around sea height is around 1.2 meters, and swell is around 0.8 meters. In 2014, Allegrino explained that 2 peak spectra are the most very common spectra in the Rio de la Plata estuary, and Tomasini and Cáceres in the same year suggested that a period of 6 seconds could be the best to separate seafront swell. Summarizing, at the present, we know that first, waves in the Outer Río de la Plata are usually a superposition of swell and sea, where spectra can be composed by 1, 2, 3, up or up 4 peaks. And then sea height are usually higher than swell heights. It's important to highlight that all these studies were carried out without the consideration of wind data. They are only work with wave data. Some questions we stand for the present work. The first one is related with the wave parameters, heights, periods, and direction of the swell. The second question is about the frequency of the swell in the Outer Río de la Plata. The third one is connected with the seasonality of the swell in the Rio de la Plata. And the fourth question is, can global wave model discriminate from sea swell in the Rio de la Plata mouth? In this work, we use wave data series in the Rio de la Plata obtained by means of a directional buoy data well where rider Mark II between 1996 and 2000. This is the position of the buoy with the blue triangle. This is the buoy in yellow. The position of the buoy is in the middle of the imaginary line that joins Punta Rasa in Buenos Aires and Punta del Este in Uruguay. In the lower right, you can see the performance of the data acquisition is rather regular, where the white zones represent the gaps of data. In the upper left part of the slide, you can see the directional resume of the data of waves. So this is the most important direction of propagation. The estuary is faced to the southwestern Atlantic Ocean in this direction. And following this main direction is there is the east and south direction. And this picture represents the two-dimensional distribution of heights and periods for the recollected data. We detected two zones in high periods. We named swell, and in low periods, we calculated like sea. But we, at this moment, didn't use wind data. But in the present world, where we incorporated wind data from Jorge Newbery Airport in Buenos Aires and Carrasco Airport in Montevideo. The directional distribution of wind are pretty similar in both locations because they are separated no more than 250 kilometers. Perhaps this is the core of our presentation. Here we present the criteria we use to select the event of swell at the Rio de la Plata estuary. The first one is about the period. They should be greater than 8 seconds. Secondly, height should be greater than 0.5 meters. Thirdly, the difference between wave and wind direction should be greater than 90 degrees. And fourth, the direction of the wave should be steady at least during 10 hours during the event. Here is a representation of the situation. In red is represented the wave direction, and in the gray zone we draw the wind direction in blue. Here we present a synthesis of the results. After applying the 4 criteria, we detected 59 events of significant pure swell or dominant swell at the Outer Río de la Plata. They are characterized by periods between 9 and 18 seconds, a maximum swell height of around 2 meters, and maximum duration of the event is 38 hours. For each event, we obtain the date, the duration, the ranges of periods, heights, and directions, and the characteristic of the wind, the mean wind in Carrasco and Aeroparque Airport. In general, spectra have only one peak. In this case, we didn't no problem because we integrated the whole spectra from low frequency, the whole frequency band. But when the spectra have 2 peaks, we divided it into zones. In low frequency, the peak corresponds to the swell and integrated from the first frequency to the minimum of the spectra. We calculate the zero spectral moment in this way, and the spectral height of the swell using this formula. The period of the peak obviously was obtained by means of the inverse of the frequency of the height of the peak in low frequency. Here we condense the whole result of the event selected, characterized like swell. In the upper left of the slide, we can see the histogram of heights. The maximum is located around 0.4 and 0.88 meters. Periods is around between 11 and 15 seconds. Direction of swell is mainly from the southeast and south-southeast, and this is the dimensional distribution of periods and heights. We present only for illustrate one of the cases. The event was we have the longest duration, 38 hours. We present the wind in Carrasco, in Aeroparque, and a closer node of NCEP 1 respect to the buoy. And in this figure, we present the direction of wind. You can see that the wind is practically opposite to the waves direction. The height of swell decreased from 2 meters to 0.6 meters, and periods is between 13 and 16 seconds, and direction of wave is around 127 degrees. Here you can see the spectral evolution of the longest event of swell in the Outer Río de la Plata. This spectra corresponds to a spectral height of around 2 meters. It decreased from this energy to approximately this in 1 day, and in this case the height is around 0.6 meters. Then since this point appear a very little high peak in low peak in higher frequency, corresponding to a young sea in the Outer Río de la Plata. In order to understand the atmospherical situation vinculated with these cases of dominant swell in the Outer Río de la Plata, we selected the pattern, the atmospheric pattern of every case. The first one represents 31 of the 59 event correspond to a very low surface pressure gradient. You can see here the lines of equal pressure and the isobars are practically very separated, and winds are practically calm. As a matter of fact, the wind is very weak from the north. The second pattern correspond to a high pressure system located at the east of the Rio de la Plata estuary, 18 from 59 events. In this case, a strong wind coming from the north is present in every event of this pattern. And the third one corresponds to a high pressure system located at the estuary, with the center practically on the estuary. In this case, the wind is also very weak, practically calm, but wind strictly have a component from the north. About the annual variability, we studied the seasonality of the event of swell during 1996 and 2001. Swell is most probable during the winter, with 33 cases in 5 years. It's practically absent during the summer, and in fall and spring is really equal, with frequency or number of cases of around 13 or 12 respectively. Finally, we evaluated the performance of 4 wave global models. They are Waveries, IFREMER, ERA5, and NOAA HENCAS 2. We analyzed the 4 analyses, and we conclude that Waveries is perhaps the model which show the best, or is the model that capture best the wave parameters at the Rio de la Plata mouth. Here you can see the scatter plot of heights from the analysis in ordinates, and the measurements are in abscissa for heights and for periods. The correlation coefficient is around or higher, a little higher than 0.9 in both cases. Then we separate, or we use the capability of Wavery to represent the swell in the region and compare with the measurements we have in the Rio de la Plata. We obtain that swell represented by Waveries versus swell, observed swell is very good representation with a correlation coefficient around 0.8. Then, when finally I present the remarkable conclusions, we obtained 59 events of pure swell or dominant swell in between 1996 and 2001 in the Outer Rio de la Plata. The most probable probable characteristic of swell are for heights between 0.4 and 0.8 meters, about periods between 11 and 15 seconds. The predominant propagation direction of swell is visibly from the southeast and following from the south-southeast and east-southeast. Practically the 90% of the cases come from this direction, because the Rio de la Plata estuary faces to the South Atlantic Ocean in this direction. Winter is the season when where the probability of swell is higher, and we can see that the calm situation, a relatively calm situation, 40 from 50 events are the more common atmospheric pattern at the Rio de la Plata. Finally, the performance of 4 global models was evaluated, and waveries show to be the best for capturing the wave parameters, including swell parameters. Thank you very much.
Okay, we have time for a few questions. So I have one. So you say that waveries was the best model to capture the waves. So how do the other models perform? Are they too bad, or are they?
They are very similar. Waveries is the best for a little.
Thank you. Okay, thank you. And let's welcome the next presenter, Yuri Brasil, that we talk about wave spectrum extraction from complex SAR images using a quasi-linear approach.
Hi, everyone. My name is Yuri Brasil Correa. My work is called Wave Spectrum Extraction from Complex SAR Images using a Modified Linear Approach. On the program is written quasi-linear approach, but it's my fault, sorry. And I'd like to thank some of my colleagues, Nelson Violante Carvalho, who's here, and Jesús Portilla. Well, in 1995, Engen and Johnson, they proposed a nonlinear transformation relating wave spectrum to a SAR cross image spectrum that was related with two separated images from a fraction of time of SAR, and this yields in a complex image with real and imaginary parts. And the real part, you can see that it has 180 degrees ambiguity. So you can see two peaks facing each other, and you don't know which direction the waves are coming. So in the imaginary part, you see a positive peak, and you can rely on that to solve this problem. So as you can see in this case, the wave spectrum is the direction is northeast. So you can solve the 180 degrees by using the imaginary part. And in 2021, we proposed a simulator of this transformation just to see those features and test any inversion scheme that we want. So a way to summarize the cross-spectrum function, and that is quite complicated, but we are just putting in a simple way. We have a product between cutoff exponential decay right here and linear transformation plus higher order non-linearities. If we approximate the cross spectrum to a linear transformation, we can get an analytical inversion, a linear inversion that was proposed by Schulz, Tellenflath in 2003. And it's quite simple. Well, we know that we are not taking into account the cutoff factor and the high order nonlinearities. So we know that this is really limited. But if we use the simulator to simulate a lot of cases of different wave systems, do the nonlinear transformation, and then apply the linear inversion, we can compare the retrieved wave spectrum to the one that gives rise to the cross spectrum simulated. And we know the limitations, but so we can model the errors associated. And maybe we could correct the retrieved wave spectrum using those errors. So that's what we did. We simulated 468 unimodal test cases. And those cases were wave spectra combining significant wave height and peak wavelength for 3 different directions. Those directions were 0 degrees, that was related to the azimuth direction, which is the flight direction of the satellite, 45 degrees, the intermediate direction, and the 90 degrees, which is the range direction, which is perpendicular to the satellite flight. But so we applied the linear inversion to those 468 unimodal tests, and we imposed certain conditions to those retrieved wave spectrum. The HES obtained must be at least 20% of the imposed HES, and the peak wavelength must be plus 200 meters or less 200 meters of the imposed peak wavelength. And we didn't impose any condition for the peak direction. So we let the wave spectrum rotate freely. Well, this is a retrieved wave spectrum. And we propose also a parameter called p-cut, that it is relative distance between the peak wavelength here and the cutoff wavelength. So if this distance it's positive, the p-cut will be positive. And we also we are just looking for the relative differences related to the HS. So we put, this is a plot with the errors associated with the linear inversion. So the vertical axis is the difference, the relative difference of the HES. So you can see here that we have minus 20%, 40%, and 80% of decay of energy. And on the horizontal axis, we have the p-cut. So between 0 and 1, we have a region that we call the linear, that's the associated with swells. And we have a lower cutoff, and the wave spectrum is more linear, more we can use that function approximated with a linear function. But even though for azimuth and intermediate direction, we have a really sharp decay, but we have a smooth decay for range direction. So now that we have the errors and we have the equations fit to those errors, we can correct the retrieved wave spectra in real cases. So we decide to apply that on Envisat ASA level 1 cross spectra from a track from ESA, sorry. And we would compare that with the ERA 5 as our reference. So, and then we compared with the ESA's inversion that's called WVW, and see which one performed best. But now we are dealing with actual SAR images. So we need to apply certain tests and filtering procedures. So the first thing we do is homogeneity tests. Then we filter non-wave features. Then we partitioning the SAR image cross spectra. We separate the what we think that it's the different wave systems, but in the SAR image cross spectra. And then we apply the linear inversion. We do that separation to treat the actual SAR images as we treat the simulated cases, that they were unimodal cases. And then after that, we apply the empirical corrections. So in our left side, we have the linear inversion method with the correction. And on our right side, we have the WVW. So the correlation that we got was 0.87 and they got 0.94. We have a small bias compared with them. The RMSE is 0.45 meters. They got 0.34. The scattered index is 0.345 and they got 0.267. So although we have good results, they have better results than us related to the parameters. And we are just comparing the HES of the part of the spectrum above 10 seconds because we know that works better for swell. So we're just trying to be fair in these comparisons. So we did the same for peak wavelength, and we have a better correlation, but the other statistical parameters, WVW perform best. So here's where the linear advantage showed some advantage comparing with the WVW. We proposed a numerical indicator that's here, omega, and here. And what is called EVA, it's related to evaluated spectra. So here can be the linear inversion scheme or the WVW. And for the reference is always ERA 5. So the closer to 0, the better. And here the green diamonds are the ones that we apply the linear inversion, and the red circles are the ones of WVW. So we have a better performance on this because the average that we got for omega is 1.13 and WVW 1.33. But the thing it's the most important with this numerical indicator was the 180 degrees ambiguity, because with our method, we solved all those cases. We know that we are just applied that on a small track, but for all those cases, we got that solved properly. And WVW has almost 1/3 of the cases with 2 peaks. And you can see them with the black circle around the red circle. So 1/3 of the cases you see the wave spectrum with 2 peaks facing each other. So just a summary and conclusions about this method. Those equations, and I did just not for the HS, but the peak wavelength and the peak direction can be used as lookup tables. So you look those equations and see how it fits and corrects the spectrum. So we can we rotate the spectrum, we shifted, and then we rescaled to keep the energy net, right? And it keeps the original shape. That's the main advantage of this method. We have slightly larger values of RMSE and scatter index, comparing the linear inversion to WVW. But if you are thinking about the spectrum shape, our shape, it's much more similar to those of ERA 5 than WVW. And the ambiguous propagation direction was not solved in 1/3 of the cases just of that track. And another conclusion is that that method is comparable to the ESA's method because it's really simple, straightforward, and doesn't need any a priori information. And we're still working on that. And we just published this work less than a month ago, and you can see that on this on the paper on the internet. It's just published, and here's some of the reference that I cite here in the presentation. But thank you.
Thank you, Yuri, and congratulations. Actually, you know that before, several years ago, we were trying to use SAR data for applications, basically. And we always realized that there is this problem of the ambiguity. And also many cases where this ambiguity is badly resolved in the ESA data. And somehow we gave feedback for a very long time, and then hoping that they will correct, or they will come up with another way of solving that. But so far nothing has happened. In the meantime, I gave up, and also I gave up trying to use SAR spectra, which is a pity. And then, you guys are doing this very nice job. So. Looks very promising, and so my question is what's next, and especially how far we are to obtain a product that it can be useful for applications.
Well, the next step that it's going to be my PhD, it's propose another inversion scheme, but analytical scheme, trying to include the cutoff decay somehow, because we are losing so much energy during the linear inversion, even though we are trying to correct that. And we're thinking, because when we are applying that on actual SAR images, we need to do some filtering and a lot of procedures. And we need to take care to don't taking off any energy. And we are just trying to do that in many cases with the Sentinel and the Envisat as well. So you see that we did that just for one track. We need to expand that for a lot of data, so that's what we are as a group trying to do as soon as possible. So maybe the next few years, don't know.
Thank you, Yuri. Nice presentation, and I know it's a difficult problem. My question is regarding the shape of the spectrum and the diminishing energy that you obtain, and also you didn't show anything related to the direction of propagation or direction associated to the spectral peak. So my question is, have you done anything related to the comparison, related to the spectral peak associated direction?
Yes.
Hold on. And this particular thing, the main direction of propagation and the decreasing in energy, might be related to the effect of short wave directionality. This is some work that we did a long time ago, when you consider the short wave, which are the Bragg waves, the reflectors for microwaves, if you consider that the Bragg waves or the short waves have a directionality, pronounced directionality, they might affect the spectrum obtained after the inversion, the ocean wave spectrum, because this asymmetry in the shortwave directionality spectrum associated with or related to the azimuth, the direction.
So when you say the short waves, you mean the waves associated with wind C?
Well, very much related to
Yes.
the Bragg waves, these very short waves. So if you consider the directionality of these short waves, depending on the relative direction to the azimuth, wind with respect to the azimuth, then it will shift the spectral peak and reduce the spectral peak.
Yes, yeah. We did for the spectral peak as well. It's just not in this presentation, but we did the same equations, but they are linear, not exponential. But yeah, we saw that we saw the retrieved spectrum rotating to the range direction, so we could correct that as well, because the absence of the cutoff factor, and for wave systems that are dominated by wind C, so we have this effect much more dominant. So yeah, answering your first question, we did for the peak direction as well, and we are quite aware of this effect too.
Okay, if we don't have any other questions, thank you, Yuri.
Thank you.
And let's welcome our last speaker of this session, César Esparza, who will present projections of stream sea levels at Cartagena Bay, Chile, towards the end of the 21st century under RCP 8.5 emission scenario.
Well, thank you for invitation. Today I will talk about my master thesis, and now I'm a PhD student, but we present some extreme sea level projection under the climate change context at the Cartagena Bay. Well, my advisor is Rodrigo Cienfuegos from Pontificia Universidad Católica de Chile. Well, Cartagena is located at the central zone of Chile, approximately 33.5 degrees of south, and is characterized because it's one of the most anthropized by urbanization zone, and also we have some ancient dunes, but at the back of the dunes that is the urbanization, and also we have some coastal wetlands with a great, very big biodiversity, and well, in the last 10 years we have many coastal inundation. For example, here is the southern part of the Cartagena Bay. We have some impact to the walls or to the back walls in the back beach, and some overtoppings, and also we have some overtoppings due to what. Overtoppings inside to water body of the wetland, and that caused some problems in the biology. For example, some migratory birds, for example, was impacted due to a coastal inundation. And also in Cartagena, we have one of the largest ports at the south of the Cartagena. We have one of the largest ports. It's Puerto San Antonio, and also in the last 10 years was affected, and the downtime increased due to extreme sea level, due to inundation in the infrastructure. And well, how to approach this problem? because we have a multiple scale phenomena in the context of climate change, because we have a sea level rise, and sea level rise is a global scale phenomena due to, for example, melting ice sheet in Greenland and Antarctic, and thermal expansion of the ocean, and land water storage also can increase the level. And also we have a regional effects, because the gravitational, for example, when the ice sheet melting, we have some mass redistribution of the ocean, and also that affects a region in a regional scale the sea level. And particular phenomena in Chile is because we have a tectonically active zone, and that produces for example, the relative sea level can change abruptly. And well, this is not included in our research, but this is an issue in our projections. And we need also to include all this process and the rapid oscillation of the sea level due to a storm surge or waves and tides. How to do that? Well, we use the global climate models. And this is the coupled model intercomparison project, and we use only 6 models. Why we use only 6? Because we drive models like WaveWatch 3 and ATCIRC in order to obtain the wave climate and the wind-driven circulation. And this is the summary of how to obtain extreme sea level. We drive the 6 global climate models, and we calculate, for example, we use that as a proxy of extreme wave height, the 12 hours exceedance per year, and we compute the difference between in each model. We compute the difference between the 12 hours exceedance per model for the projections minus the historical period. The global climate model includes a historical period. It's not like our analysis. It's only for climatological purposes. And also after when we calculate the difference per model, also we ensemble in a median, and this is the global pattern of wave change. But this stage only is for try to identify the pattern, the global pattern of wave change, and in a Pacific scale. But also we need to make some the dome scaling to the Cartagena Bay, and we extract the spectral for each model. We simulate 6 models for 2 periods between 1985 and 2004 and 2081 and 2100. And we extract the spectral information, and we propagate all the spectral information to the coastal, some virtual buoys at the coast. And in the ATCIRC model, we simulate the wind-driven circulation, and for the same models, we extract the pressure, the mean sea level pressure, our winds, and we simulate and we extract this component and the height due to a storm surge. And also with the coastal propagation node, well, this was developed with the STIWave model because it's a very fast model. We construct on the basis of additive linear model and the total water level, and this is composed by run-up, storm surge, and also the mean sea level rise yearly data. And in order to include the astronomical tide, only we use an average in a metonic cycle, because the astronomical tide is an independent phenomenon. and how to transform the ocean waves from the deep water to shallow water. Only we use the a transfer function. We compute using the Steway model, a transfer function. We apply this to the spectral in order to obtain all the active component of the spectral and solve because we have a closed bay and we need to solve all the component of the spectrum. It's a simplified method, but we make some downscaling in a laptop. And well, the nearshore time series was transformed to a run-up time series. Well, we use the Stockton formula, and the Stockton formula is in function of the slope of the beach. We transfer. We use we transfer information from the deep water to 6 beach inside of Cartagena Bay, and the beach slope we use a tool developed by Kilian Boss called COSAT slope, and we compute the slope of the beach. This tool is use the satellite image, an algorithm is kind of a Fourier transform, and he derived the coastal slope due to a motion of the coastal line. And finally, we compute the projection of historical level. Sorry, here this is the historical level. We include the wave run-up, storm surge, and only average tide, average high tide in the metonic cycle. And in the end century projection, this is wrong. This is the end century between 2081 and 2100, and we include the sea level rise. And here we can compute what is the inundation, the inundation elevation, flooding elevation. And we have some issue here because the time series is non-stationary. And we need to apply the extreme value theory. And the extreme value theory was derived under the basis of stationary time series. And we use a method developed by Lorenzo Mentacci. And it's a very simple method because we normalize time series, we detrend and divide by standard deviation. And we can remove the non-stationary behavior. The method is called transformer stationary, and we check if the time series transformed is stationary, checking the high order statistics with skewness or kurtosis or high orders. When we have a stable high order statistic, the time series is stationary. We applied the extreme value theory to the transformed stationary, and we compute the return levels, and also we make a back transformation. Well, the results in oceanic scale, the wave at oceanic scale is characterized due to a increasing in the high latitudes. The ocean at the end century we will increase, but at the mid latitude between 30 and 40, the wave height will decrease, but the mean wave period the mean wave period we will increase because the wave generation zone where we will shift to the south, and this produce also a counterclockwise shift to the in mean wave direction. The waves will be propagated from more to the south with more southerly the directions, and that at end century. And when we use the Stilwell model to reduce the scale of global climate models. This is a measurement of inside of Cartagena Bay, and our methods to make downscaling is a good. We have a good agreement with a measurement, and well, this is a summary of a run-up, and this is very interesting because in the southern part of the Cartagena Bay, we will have some decrease in wave run-up components. In the northern part, and we have some little increase, but in the central part of the Cartagena Bay, the run-up will increase. This is due to a wave period will be longer wave periods, and this can impact directly to the wave run-up component. And also this because the formula, the Stockton formula, is scaled with a wavelength, and also that is an issue because maybe this formulation will need to be corrected because, for example, doesn't account the infragravity waves as a function, for example, beach slope, and this is an issue also in the formula. But this is empirical formula, and we can derive a proxy of wave run-up. And storm surge with a tilt model is in Chile, in particular in central southern Chile, the storm surge is not a relevant component to the coastal faultings. Here we show the historical storm surge component 0.25 meters, and the mean and the max global climate model in ensemble member. And in projection at the end century, the storm surge we will a little increase at the end century. This is we have some hypotheses, but I will talk in a few slides why this produced. But when analyzed at the shorter return level, also we see some decrease in the storm surge component. And this is the sea level rise in Chile. We expect 65 centimeters, plus and minus approximately 0.4 meters. And this is due to uncertainty in the component of the sea level rise. And the extreme sea level in all parts of the Cartagena Bay. This is the figure. In all parts of Cartagena Bay, we will have a increase in the extreme sea level, but the increase is due to the main contributor process to the increase in extreme sea level rise towards to the end century is due to a sea level rise. But in the central part of the Cartagena Bay, we have some accelerated or above the mean sea level due to in the central part we doesn't have a shelter, and this can amplify the wave run-up component. While in the northern part also we see the same level approximately due to a sea level rise. Well, this is a qualitative map to try to cross the 10 meter above mean sea level control line and the extreme sea level, the total water level during the extreme condition. And well, in the historical period, we see in the central part of the Cartagena Bay some intermittent wetlands when we have extreme sea level, extreme waves particularly. Some intermittent wetlands, some intermittent water bodies was formed after the event. But we think under the basis of this projection, this intermittent coastal wetlands will be permanent coastal wetlands. And in this part of the coast, we have some houses, some real estate development or something like that, and this will be a problem in the future. And also the wetland will be totally flooded under the base of these projections. Very simplified, but it's a proxy. And well, in conclusion, the tower of the end century, the storm wave generation, we gradually move to the higher latitudes. And well, this is due to a poleward shift to the storm belt. The storm belt will be generated in higher latitudes, and this will induce a longer swells. In Chile, now we have a very long swell between 18 and 20 seconds, but at the end century, the swells component will be more longer, and this can impact the coastal forests. I'm sorry. And the mean wave direction, also we tend to shift to counterclockwise rotation at the 33.5 degrees, approximately 3 degrees, and also this can impact in the closer base, because the shelter will be more effective. For example, in the bays oriented to the north, for example. And well, this is an hypothesis, because these are little decreasing in the storm surge component. Rikaczewski, I don't know how to pronounce this last name, but he has some hypotheses related to the Pacific subtropical anticyclone, and the Pacific subtropical anticyclone will move to the south, and this will block the central zone storms, and that is a main cause of for example, the drought in Chile now, and also the decreasing in the low pressure system in the central zone of Chile. And in the shelter sectors, in the southern part of Cartagena Bay and the northern part of Cartagena Bay, the stream sea level amplification we will in accordance with the mean sea level rise projections. The mean sea level rise will be the main process in the increasing in the stream sea level. But in the central part of Cartagena Bay, due to an increase of wave periods, we will above the extreme sea level projection will be above of the estimated sea level rise. The estimated sea level rise, we need to include the wave run-up component. And well, this is also kind of a hypothesis, because we use an empirical formula. We need to validate this hypothesis with a model based on process or physical modeling. And well, this is another important issue is Chile is a tectonical active zone, and this projection can be amplified because the sea bottom can change due to a earthquake, for example. Well, and this is my PhD research in Chile. In able to make some adaptation of the coast, we will use rubble mound structures, and we have an hypothesis related to the climate change scenario. Sea level rise and longer waves can trigger the infragravity waves, and we have a hypothesis related to the infragravity waves is plays in a role in a maximum wave overtopping, in the violent wave overtopping. And this is the paper of Hofland, and he shows that the mean wave period at the toe of the structure drastically increased, and that contributed at wave overtopping. Thanks.
Thank you, Cesar. It's an impressive amount of work for a master thesis. You've done everything from waves to climate modeling.
Thanks.
My question about the future wave modeling, right? So you take winds from the climate models, right?
Yes.
But climate models that usually low resolution winds. So
Yes. This is an issue because in Chile we have some coastal winds, and yes, it's a poor resolution but we use the CFSR and that is not included in my presentation, but we use the CFSR simulation, and we correct the bias via quantile mapping. But this is the best of the best product.
That's
but
important. So you have
we need
solution even for that. Yep.
We need the regional climate model here in Latin America. We don't have regional climate models.
Okay, thank you.
Thank you, Cesar. Very, very useful work. For me, a quick clarifying question. You show the time series with the trend, and I just couldn't read the x-axis. I don't know how long is the time series because
in the extreme value normalization.
Yes. That one.
Here?
That one. Yeah, because the trend is so strong.
Yes, because
what's the axis? What
no,
scale?
this is the year. The year between 2000 and 2081 and 2100.
How many years? Sorry?
20 years, because this is the last part of the in this time series we mix all the components, and this include the mean sea level rise. It's not pure ocean waves. It's a total water level time series.
Okay.
This
Yeah, because I see that the
increasing. Yes.
The trend is very strong.
Yes.
Okay.
Yes. This method is try to remove that tendency in order to make the steam value theory.
So in the red signal there is the sea level rise considered, right?
Yes. Here we consider the sea level rise, the run up, all the process we mix in a one proxy called the total water level. Run up, mean sea level rise, storm surge, astronomical tides.
Okay. Yeah. Thank you.
Hey boy, a lot of work. Congratulations.
Thanks.
I want to see the last slide. You mentioned an important result. You said that the storm wave generation zone will gradually move to higher latitudes. That
Yes.
worry me. May you tell me more about it? How far this zone will move to the north?
I am not climatologist. This is a climatologist issue, but the response of in the ocean waves and is a change in the mid latitude bands, and increase in the high latitude bands, and also that is correlated to the south shift in the wave directions. And here is the projection minus the historical 50 percentile mean wave direction, and you have a 5 or 7 degrees, and this is a sign of the wave will be generated in high latitudes. We translate to the high latitudes, and the directions will come from more southern. And this is in accordance with a publication with a big number of models. Only we use 6 models, and we can reproduce that pattern. But for example, Morin, he used I don't know 30 models.
Gotcha. Thank you.
Okay, thank you, Cesar, and all of the speakers of this session. And we have the lunch break now.
discover I'm your chairman. I'll be very tough. No. No, with you much worse with the other one. Okay, let's start. And I apologize, I completely forgotten I was going to be the chairman. Terrible. No, I thought that there were 2 sessions today. I knew I was not the last one. Okay, Frederick. Role of ocean wave in numerical weather prediction. Is that correct? No? Ah, sorry. No. Maybe good, terrible. Mamma mia, Frederick. Coastal boulder deposition. Yes. Frederick, you have half an hour. I'll raise my hand with 5 minutes to go.
Thank you very much. And first of all, I would like to thank the organizers of this wonderful conference. This is my second one, and I've enjoyed both a lot. So the title is indeed, well, that's on the program, Coastal Boulder Deposition. But actually, there are going to be 4 parts in the talks, and so this will be only one of the 4 parts. But don't worry, I will try not to go over time. Also, so my affiliation, so I was in Ireland with an affiliation in France, and now I am in France with an affiliation in Ireland. So I still have both affiliations, but I'm mostly in France and about 1 week per month in Ireland. So, and that's, so here I explain the setup of our group. So about 15 scientists in the group, and then we decided to call the 2 teams, the one in France, the Navier team, and the one in Ireland, the Stokes team. Also, I have a full-time engineer based on the west coast of Ireland, and also that's where we have our workshop. And then we have a research station that we built from scratch on the Aran Islands. So in terms of locations, so that's Paris, that's Dublin, and that's the west coast. And then if we zoom on the west coast, then this is where the workshop is, and then there is this 3 islands, and we are based in the middle one, Inishman. And also I'm going to show some lab experiments, and they were performed in Marseille. Now this is a slide from the conference 4 years ago in Colombia. And why I'm putting this slide is because at the end of my talk, I said, you know, I would like to recruit a 2-year postdoc in UCD, and that was to work on the resource code program that, and Leandro was at the conference, and then he contacted me, and then he was the hired. So that's the first connection now with this Latin America conference and community. And so, by the way, this was a successful project. And so Leandro talked about the paper we published. And also, the main goal of the resource code was to produce this high-resolution wave parameter dataset for the European Shelf and Analysis Toolbox. And there is the link at the bottom if you're interested. This is really a fantastic toolbox. So, as I said, 4 parts. So now I have some funding from the EU, and the name of the project is HighWave, so I will say a few words about that project. And then I will talk about some previous work in the lab on subaerial boulders. then some present work on underwater boulders, and then at the end, Luigi mentioned theory, and so something that, well, I hope you will find interesting, but I don't know myself. So the this project HiWave, it started in 2019. It's for 5 years. Probably it will be for 6, because you can imagine that the pandemic, and Brexit didn't help in for this project. So it has 4 work packages, and the first one, I call it breaking onset and dissipation. So we want to include, to improve the inclusion of wave breaking physics into operational wave models. The second work package is, I call it breaking wave loads, and I will talk about it today. And the third one, I will also talk about it, breaking wave erosion. But here, by erosion, I'm not talking about sand erosion. I'm interested in the motion of small boulders, typically of the order of a kilo or several kilos. And the fourth work package, a new approach to field measurement of breaking waves. And this is where we spent quite a bit of time because we had to get everything built from scratch. So I will talk about this. Here's the team at the bottom, and there are a couple of names in red. So again, that's a connection with the with this community here in Latin America. Lucia used to be at CICESE, and now she's a postdoc with me. And Danielle is from Colombia and is a PhD student. And also, this project has several collaborators outside of my own group. So here's the list. I'm not going to go through all the names here. So, as I said, the research station is based on Inishmaan. This is the Irish way of writing it here. And so, well, it's a project on wave breaking. So we would like, to do some measurements related to wave breaking. So this cartoon here is an illustration of the some of the sensors we are using. So there is an ADCP. There is a conventional MedBoy. Possibly, if we still have enough money, with a hydrophone. And then also here I will explain what we are going to put in this. So some camera, and actually 2 cameras to do stereo vision. And we have obviously a weather station. It's clear from all the talks in this conference that, the wind is important for this type of studies. And also, more anecdotic, we also have a seismometer. And actually, when the waves hit on the cliffs, and we have some very big storms, the cliffs vibrate, and so we have some interesting measurements as well on this. And also we have a pressure sensor, and we also have some low-cost buoys, some spotter buoys. So now an illustration of what I'm talking about with this station. So this is the what we call the mobile research stations. There are some wheels, so it can be moved if needed. And then, so the electricity is generated by solar panels. We also have some wind turbines. And then this is the weather station. This is what we call the mini pod, where, for example, here there's a camera inside. And these are the 2 pods where we are going to put the 2 cameras. This is almost ready now. It's all cabled and so on. So they're on top of a cliff. Now, of course, I mentioned that we are going to put this conventional MedBoy about 10 kilometers offshore. And so we need a permit for that. And this has been a nightmare. We counted the number of hours we spent on that to more than 200 hours. The application itself was more than 200 pages. Several times we were about to give up. but now it's in the on the desk of the minister for signature. So I doubt that this minister is going to deny the application. Also, something interesting about the project is that we are using the CFI concept. So to get the data from the buoys, for example, through Wi-Fi, and so we don't use satellites. And so this cartoon here illustrates, well, and the reason why I put this, Luigi mentioned, the terabytes of data. So we are, and there is also the radar on top of the container, which will, provide some data. So we'll have a lot of data, and I will say something about this later. I know that several people asked about the radar that we have. So it's a Ku band polarimetric phased array radar. It's a frequency modulated continuous wave type radar. So it's different from the usual marine radars, and it's a coherent radar, and so we can obviously, obtain the Doppler velocity of the waves, and as well as the backscatter intensity. The total azimuth coverage of the radar is 91 degrees, and the radar will be mounted on top of the research station. So we have the radar. We got it a couple of months ago. So right now we are testing it along the shoreline, but this should be operational soon. Now, I like this photo or this image very much. That's a SAR image over Inishman with a long swell on the 1st of February 2021. So Fabrice Collard from Ocean Data Lab, who looks at SAR images every day, found this one, and he said, Frederick, this is the best I've ever seen. So that shows, I don't know if it's good news or bad news, that of course, the wave situation is quite complex around the island. But we have obviously, one thing I didn't mention is that if you look at the west here, then there is no filter. The next port of entry is the US, and so we get really all the storms, without any filter. So it's quite energetic. So we have obviously some swell, we have wind waves, we have some refraction, we have some reflection, we have braking. So we have everything, and every time I go to the island, I spend some time just looking at the waves. To me, they are never the same. But that's really fascinating. Okay, so I'm done with the introduction of the high wave project. So now I'm going to talk about 3 little sub-projects in this. So the first one is the displacement of cliff-top boulders by breaking waves. And so again, we have an illustration of the west coast of Ireland here. So there are some examples at several locations, but again, we are on the Aran Islands, and especially on Inishman, the middle island. By the way, that's what it means in Irish. And also, so this is really phenomenal. There are some big boulders that have been moved, and I don't have time to go into the details, but initially people said only tsunamis have the power of moving such boulders. But there is not much evidence of big tsunamis in the area, but we definitely have big storms, and especially the winter of 2014, where we had one big storm every week. So we have evidence that some of these big boulders have moved, and actually Rona Cox, who is based in the US, but she's Irish, she has a catalog of all these boulders that have moved. Here we go. So this is, not the dimension here, it's the mass, but if you, and so this is from Rona Cox observations. So what we have here is the boulder mass probability distribution on the Irish west coast. So this is the mass. So here it shows the 1 ton boulder. And so we've been concentrating on this one here, a 210-ton boulder, which we know has moved. And so then we decided to try to do it in the lab. So at a scale 1/30. And so this is the small boulder that we built. We call it a smart boulder because we put sensors in it, a pressure sensor, and also accelerometers. So before I go into the results of these experiments, let me show, the one that fascinated me. Now, we built this 1/30, but we also built a smaller one. But the smaller one, we couldn't put sensors in it because it was too small. So about, of the order of 1 kilo. But there is evidence that when these boulders have moved, there are all types of motions, just moving in translation, flipping, rotating, and so on. So here you have some evidence of some flipping. So these are lab experiments, as I said, performed at the École Centrale Marseille. And so here's the focused wave coming and the flipping of the boulder. But as I said, this one is not, doesn't have any sensors in it. So now going back to the 1/30 smart boulder. So this is the tank here. So you have all the dimensions. Then this is the wave signal that we input. So the idea is to focus waves at some locations. And so essentially I'm going to talk about this XF, which is the focal point. And XF is 0 means that the wave focuses right on the cliff. And if it's negative, it focuses before. And if it's positive, it focuses on top of the platform here. And this is the boulder, the smart boulder with the pressure sensor and then the accelerometers. Also later, I won't have time to show it today, we also put 70 pressure sensors along the vertical wall to really understand the impact. So here on this diagram, what you have is, so the focusing here is quite negative. So the wave focuses away from the before the cliff, and then at 0 it focuses at the cliff, and then when it's positive it focuses on top of the platform. And on these you have the pressure measurement, and you also have the acceleration. That's the solid line. So I'm going to select 3 of these to show the difference and the effect of the shape of the wave when it impacts the boulder. So the first one here, where the wave focuses before it reaches the vertical wall. So it's working. The water level is rising here. So the wave is now overturning, and then it's impacting the block. So of course, what's really exciting in this type of experiments is that the first time you run it, you have no idea if the boulder is going to move or if it's going to not move at all and during the whole set of experiments, or move too much and then break something. So we were lucky that that it moved as we expected it would move. Well, at least in terms of a few centimeters. So let me go to another one now, where the focusing is at the cliff. And so here, we are using a fast speed camera. So now it's just, so that's a different type of motion. There are a lot of things that we observed as well. And remember that, this is, the water is going on the side of the boulder. So the boulder only occupies 1/3 of the channel width. And the last one now, the focusing is on top of the platform. So it's it should be coming. This one is a bit slower than the others. Yeah. So now the wave has not broken yet. And still there is a little bit of motion. So then, just to finish on this part, essentially, you know, we did the largest waves we could do in the wave tank. So then we tried to find, you know, what HS that would correspond to. So then the three types of runs we did in terms of wave amplitude are these three dots in terms of the HS. So independently of that, we looked at all the cliff-top boulder displacements, not only in Ireland, but also in Iceland, in France, and some other countries. And so this is, so on this graph here, it's on the horizontal, it's essentially the boulder size, but it's dimensionless, so it's divided by this HS. And then this is the boulder elevation. So obviously, you know, if it's very heavy, then, you know, it's not going to, if it's also high and heavy, it's not going to move. So this graph makes sense. And so this, the curve here is what we found as the dividing line between all these move and above, you know, they don't move. So then the three sets of experiments in terms of wave amplitude that we did, then they correspond to the 3 points here along the, so right at the boundary. So, but in all cases except one, the boulder moved. So the main conclusions of that part, so there is definitely an influence of the wave impact mode, and we distinguish between aerated, braking, and or sloshing. The largest displacement is in the braking range, the smallest in the broken or unbroken ranges. And of course, you know, one question is, what's the similarity between the friction, for the friction between the prototype and the laboratory scale? Okay, part 3. Quickly, so now we are also interested in the motion of boulders underwater. And we know that they move. Some years ago, I was involved with some crazy, it was not an experiment, it was not science, so I'm not going to explain what it was. But anyway, there were some measurements at the sea bottom before and after winter, and this was the winter of 2014. And when they came back to collect the equipment, the divers could not recognize the place. It was like a war field. So so definitely, you know, things move also at the sea bottom, and even some large boulders. So we attack this problem both with CFD using the SPH method, and also with some experimental work in Ishman. So in terms of SPH, well, because, you know, I'm always a bit skeptic about SPH, so we use 2 codes at least, then we can compare the results. So these are the 2 codes we use. And so these are some preliminary results. The difficulty in this type of work is actually, again, to make the boulder move. So if you don't do it properly, it's not going to move at all, or you know, or it's going to go very far. So that took some time to adjust. And on this, we worked together with Corrado Altomare in Spain and Alejandro Crespo. So we're also doing some experiments on the island. So we started by selecting some boulders of different sizes. So that's the different colors. And then so we also use a drone to observe the pressure sensor. This is where we started doing it. So then we put these colored boulders in the water at low tide, and then we come back a few days later to see, you know, how much they have moved. This is really, so far we don't have results. We just set up the protocol to do it. And but here that was for fun to make sure that at least one would move. So then we put two like almost, well, not really in equilibrium, but so you see them here. So then after several hours of waves coming, we even caught the one that made one go down. So again, this is ongoing. We are working on the protocol, so the results will come at the next conference. Now, this is an interlude for Luigi. Yes, and so we are also working on the effect of rain and wind on waves, and we started with a small lake in the same area. Here, that's the lake, and so definitely, okay. There are two things. So we have a weather station and the spotter buoy. The initial data suggests that rain indeed has an influence on HS. However, even though this was in the spring, so we would expect quite a bit of rain in Ireland. But there was no rain. So actually only 6% of the data included rain. So we are very careful, we don't want to extrapolate too much. So now we are praying for rain to continue the experiments. But definitely there is an influence of rain. So the last part here, so I will try to be brief. So this is quite theoretical. Now, when you study solitary waves, so just, a single wave on a flat bottom that propagates at the speed c, and then you can increase the amplitude, and so you can follow the branch of solution. And then for water waves, when you consider that there is nothing on top of the water, then the limiting configuration is the so-called Stokes wave with a 120-degree angle. I'm sure, most of you are familiar with this. So then, if you have a two-layer configuration, then it's not as clear. And actually, there were some earlier studies saying that if you increase the amplitude, then either there is broadening of the wave or overhanging of the wave. But it was not clear, which limiting configuration occurs. So we went back to this problem, but now, having in mind the air-water interface. So initially, you might think if you take a density ratio of 10 to the minus 3, it's probably not going to change much. But I really wanted to, I was convinced that there would be an influence, even if it's a small one. And there were, the density of air was mentioned several times during this conference. So, so what we did numerically, we solved the Euler equations, and then we followed the branch of solution. And so this is for a density ratio of 0.01, so still too large, for the air-water interface. So, and we had a paper last year in the Journal of Fluid Mechanics for this. And but now we decided, to go further to 10 to the minus 3. So then in our problem, we have three parameters. The depth ratio between the two layers. So this one is not really relevant. So we took a very high width for the depth for the air layer. So this value is fixed at 80. Then the density ratio at 10 to the minus 3. And the one we vary now is the speed of the wave. But also we were intrigued by this paper in the Journal of Fluid Mechanics by Villermo and Pomo called Super Freefall. And they were explaining that, the acceleration of water can be more than gravity in some cases. But they had this illustration of this droplet type crest at the water surface. So now what we do here, so we follow, that's the branch of solution. So we increase the speed. And as we increase the, we increase the amplitude. And then the branch of solution is slightly more complicated here. And then these are the profiles along the branch. So S1, that's just, a boring solitary wave. And then you move along the branch, and then the angle starts to change. And then at some point, there is the overhang. And the last one here, S8, is this profile here. So actually, the limiting configuration is, well, that's conjecture. It's not proved mathematically speaking, but that at the end of the curve of the branch of solutions, there is the 120-degree angle, and then there is a droplet of the liquid on top. So it's not a stable situation for sure, but I was really amazed that, this is what at least the Euler equations give you. So there is definitely a strong influence, because there is the 120-degree angle, but then there is the drop at the top. So and then we built a local model here, so I don't have time for this, but essentially we can show that the size of the droplet goes to 0 as the density ratio goes to 0. So then also with our simulations, we can look at the shear along the bubble. We can look at the velocity field. And then now we are looking at the stability of this type of waves. So the conclusion on this, the limiting configuration of interfacial solitary waves has finally been sorted out. So I agree, this was a theoretical problem, but I think, there is a link with the crescent stabilities and breaking. And all this is without surface tension, just the gravity. Now, so I do the same as in Colombia 4 years ago. So I still have a postdoc to recruit for the HiWave project. So what I'm looking for is a data scientist with a good knowledge of water waves, and who will be comparing the data from the radar, the data from the stereo vision from the buoy, and as Luigi mentioned, there will be a lot of terabytes of data. So how do we deal with this, and so on. So I'm looking for a candidate interested both in fieldwork and data science. And I thank you.
Thank you for being on time. Very good. Question? I have one. And you didn't discuss this, but you mentioned that seismic movement, vibration due to waves. I'm curious because we got the same completely different environment on a beach. I wonder if it is the same phenomenon or not. In your case, was the wave hitting the cliff that was produced in the night? Not the resonance of the reflecting wave.
Well, so initially, that was the reason why, I thought it would be good to have this seismometer. Then we installed it, and we started to look at the what we observed. And actually, so there are these resonances. Of course, there are some microseisms that we see, the Longe-Higgins type microseisms, especially since we have quite a bit of reflection from the cliffs. So we get these standing waves.
What you need to have the resonance between coming and going.
And also, we have the swell and the wind waves, so we could have also some interactions. We have infragravity waves as well. So the bottom line is that maybe in 2 years I will show results, but for now the postdoc gave up. It was so complex, so we started to. So it's going to take time to really understand.
One thing I think in that your coastline may be too irregular to have a regular reflection and bitumen, because this is a work. Just to let you know, and this. Was been exploited by Fabrice Ardouin on the west coast of US, when you have a reflected wave that interacts with the incoming one, leading to a bitumen on the bottom, as this is reflected on the seismometer. So what are you actually thinking, planning, or dreaming perhaps, of using the 20th century history of seismic data in California to reconstruct the climate of the Pacific for the whole 20th century.
But we definitely see microseisms. Where they come from, it's not so clear, but we see them on the measurement.
Okay. Paco.
Thank you, Frederic. Very impressive. Just a particular question regarding the radar that you are installing. I wonder what you expect to measure with that radar and details about the coverage and resolution, for instance.
Yeah, so it's a very high resolution
KU band, yeah.
Yeah. Now we expect to get some information on wave breaking, and so I have a postdoc. You know, she works full time on this, so she's working, you know, with some other radar data, but that's the main purpose, is to try to get some information about breaking waves, and you know there are some directions to do it. Now, you know, if you talk to some people, you know, they will tell you good luck, because we don't even understand irregular waves with radar. So then to understand, you know, wave breaking, it's even maybe impossible. So, you know, it's, you know, you hear so much on...
But what are you getting from the radar? You got an image every instant?
Well, from this one, nothing yet, because...
Just one signal as a function of time.
So no, from this one, you know, we don't have measurements yet, because we still have one issue that is being solved, you know, in the coming weeks. So, but then the idea is, you know, we get the Doppler velocities and we get the backscatter, and so.
As a function of space as well. Okay.
Hi. Thanks for presentation. It's very good. I would like to make some question related to smoother particle models, because I see in the literature many researchers tends to use to simulate the overtopping. What is the difference between traditional computational fluid dynamics and particle? What is the advantage to use particle to simulate the
yeah, so the main advantage for this type of work is, you know, we want to make this boulder move. So, you know, when you have a moving boundary and so on, so particle methods are relatively good for that. If you use a traditional open form, or, you know, when you have a moving boundary, you can do it, but it's much more complicated. So that's one of the advantages. And then, you know, for the splash and the wave breaking, it's, you know, it has been used, but again, you know, it can be done with Basilisk or, you know, with some other codes, but here it was mostly for the motion of this boulder.
For the air in the breaking, when you generate bubbles, also you can simulate with a...
Yes. Mm-hmm.
Cool.
Yeah, I have a comment and a question. I'm here in another corner. Yeah, I see that fantastic, this lab experiments, visualization of what is going on. And we are working on computational fluid dynamics, NCEP fluid, which has the so-called volume of fluid, which can produce liquid, gas, and real surface tension. It might be also applicable for other cases. There are different types, like NCEP fluid, open form, that different software. In that case, it's not necessary even to program that basic Navier-Stokes equation, because they already programmed there. What is my interest about this? We are running this computational fluid dynamics, which are coming from engineering applications and are trying to use it for real ocean. But we need verification, because computational fluid dynamics, I see that has tendency to be better than the world, showing something fantastic. It's necessary always to restrain a check, and this type of lab experiment would be very good opportunity. Just we run same type of settings and see is all the splashes are exactly the same or not. Yeah, so that's great work. Congratulations.
Thank you.
Something about nonlinear interactions, as Luigi challenged us yesterday, right? But you did the completely experimental talk, right? Just a couple of comments, right? The radars investigating wave breaking. New Zealanders did a lot on in that space, right? About 20 years ago, maybe even more, right? Murray Smith is the name. It's published in mainstream journals. I learned a lot from reading their papers, right? Because it gives you an idea how it propagates in space, right? The wave breaking, and it slows down. All those effects are there. About seismograms, Gigi, it's tempting, right? And we try to do that to study climatology, right? In Australia, these seismogram microseisms records, right? You can get them we had a full PhD projects, right? In Western Australia, they studied the records from 1960s, but in the region, if you want to go far, in Malaysia, they recorded them even in 19th century, right? There is a problem, however. These days, you take seismograms, no problems to see storms far apart, right? We see almost half of the South Pacific in the east and the tropical cyclones in the west. You get them almost in real time, but the digital records, they only go back 20 years, 1990s, if you're lucky. And then you have this, this pen, right? And first of all, you have to digitize that. That's the problem. Second, the high frequency is not there, right? Is the pen is its frequency is as much as they can do. And good thing about waves that they're clearly different to earthquakes because the frequencies are different, right? But frequencies are higher, and this pen, which is wiggling on a piece of paper, not always picking them up, right? So that's a good project, but you require a lot of luck.
Well, we need fantasy, of course. And then out of 10 attempts, one will be good. But it's always good to throw new idea into the field.
Alex, I will be happy to show you some of the measurements we get. Of course, this was, the first time I was working with the seismometer. So, I was happy to discover things. And, the first thing we saw, was the big earthquakes. There was one in China we of course, we get these. So that's good. With Tonga, we also got things also with the weather station. So that was quite exciting. And but then for the rest, sometimes it's in terms of the frequencies, it looks like it does not correspond to anything. So I will be happy to show you some of the observations.
Okay, thank you very much. Now I have a bad news. Now is the time of Italian mafia. Because you have an Italian chairship and 2 Italian speakers. Giorgio.
Thank you, Mr. Chairman.
Why don't you introduce your title? Now, Giorgio Bellotti is going to talk about tsunami and how to handle them and variability, frequency along the coast. You can introduce your title.
Thank you, Gigi.
I will call your attention after 15 minutes, 45 minutes to go.
Okay. Okay. Thank you, Gigi. Hello, everybody. It is a pleasure and an honor to be here today to share some results of my research, which will be about the impact of tsunamis along the coast. Okay, so let's wait 1 second for the title so that I can explain better. Come on, Gigi, we can make a dance here.
Why don't you talk about what you are doing?
Yeah, I can. Okay, I can start introducing the research. Why not? And then we wait for the slides. Okay. So the research I want to talk about today is about the impact of tsunamis along the coast. And the very important thing to say before anything is that the level of the inundation along the coast, okay, will depend mostly on two factors, okay? One, of course, is related to the properties of the incoming tsunamis. But the other factor, which is sometimes neglected, is how the coastal area will respond. If there are some resonating modes that will be excited by the tsunamis, and that will make the difference, okay? So can I start officially with the slides? Okay, let me check if I can move, if I can use the pointer. You have to... Okay, very good. So in order to have a look at this in detail, I have developed over the last 10 years a model that is able of identifying the natural modes that resonate when a tsunami attacks the coast. So the model is based on the linear long wave equation, which is solved using a modal decomposition approach. And why it is useful, in my opinion? It is useful because it can help in understanding what are the physical mechanisms that give high inundation at some points along the coast. And it is also useful because we can identify with this model what are the places along the coast where we can expect larger inundation. So then we can use mitigation measures to protect those areas. So the model is based on the long wave equation. As I said, it's a linear one, so no wave breaking and stuff like that. And I would like to mention that I have introduced an approximate radiation condition to model the outgoing waves toward the open ocean. And this leads to have complex eigenvectors and eigenvalues that represent partially standing waves in the model. I will try to explain better later. One of the recent developments of the model is that I have included the incoming waves, so the actual tsunamis that attack the coast, while in the earlier versions of the model, I was only able, as I will tell you later, of looking at the natural response of the coast. So, very quickly through the equations, okay? I start from the linear long wave equations with reflecting and open boundaries, and including some source term to represent the incoming tsunami. And I use a finite element approximation to transform this partial differential equation into a system of ordinary differential equations in time. And then I use a modal decomposition approach. I split the solution in a space-dependent and a time-dependent parts. And using the homogeneous version of the problem, I obtain the eigenvalues and the eigenvectors of the problem. So then, using this new kind of solution, I can obtain a system of ordinary differential equations that can be solved for to evaluate how each natural mode or eigenvector vibrate in time, changes over time. So I can build this new system. And as usual in this kind of approach, I can multiply the resulting system for the transpose of the eigenvector matrix. But the bad news here is that the matrix of the system here are not diagonal, as happens in many computational approaches based on this theory. And this is due to the fact that I have introduced into the system the radiation damping. So the fact that the waves can leave the domain. So the fact that I have this damping makes these matrices here non-diagonal, and all the equations for each eigenvalue are fully coupled, okay? So this does not introduce a real advantage from a computational point of view, and the only advantage is that we can look at the physics, we can look at how the natural modes respond. If you want to have, if you're interested in some more detail, I have a recent paper here where we have all the mathematics, okay? So, applications of the model. As I told you, the earlier version of the model were only able to look in the natural response. So I have applied it with my friends and colleagues, Patricio Catalan and Rafael Aranguiz, to many locations along the Chile coast. For example, this is a paper about the resonance in the northern Chile coast, and this is about south of Chile. But as I said, we were only looking at the natural response. We have compared with measurements, obtaining very good agreement about resonating frequencies. But now the model is ready to simulate actual tsunamis attacking the coast and looking at how the natural modes will contribute to the total tsunami elevation. So what I would like to do today is to show you a couple of very simple tests, which are quite academic, I would say, but can help us understanding what is the type of analysis that we can do, what is the type of result that we can do. And work is in progress to apply this new version of the model to real tsunami attacking the coast around the world. I will tell you maybe later something. But let's start with the first test that I have done. This is the test in which long waves attack a long and narrow bay with a constant water depth. This is a very, very famous test because it is always used to test water wave models for the wave propagation into harbor. And we can especially look at resonance because if we model a periodic wave attacking the coast here, we immediately see that the amplitude of the waves at the back wall of the bay will strongly depend on the frequency of the incoming waves. And we can immediately see that there are diagrams that correspond to resonant periods. So now let me show you the application of the model. First step is to evaluate, to solve the eigenvalue problem. So to calculate the eigenvectors and the eigenfrequencies. And for example, one very important eigenvector is this one, which represents the first longitudinal mode of the bay. We have a crest here, we have a nodal line here, and we can, of course, calculate the frequency, which is exactly identical to the one at which we have the peak, of course, in the amplification diagram. And then we have, for example, another very important eigenvector, which is this. We have a crest at the end of the bay, a nodal line, a crest, and another nodal line, and etc. Okay, so we obtain from the homogeneous version of the equation the eigenvalues and the eigenvectors. Now, this is quite difficult to understand, so I will try to spend a little time on this. Now, let's look at the computation forced by incoming waves. So, first, I will try with a non-resonant harmonic wave, periodic wave. So, for example, I have tried with a regular wave with a frequency of 3, and this is the elevation at the end of the bay. And what we can obtain from the model is the time series according to which each eigenvector vibrates. So, I know could be difficult, but let's look at this. This eigenmode, which is the second longitudinal mode of the bay, is the number 256, for example, and it will vibrate according to this time series. This eigenmode, which is the first longitudinal mode, will vibrate according to this time series, okay? So, the point is that we can split the contribution of each natural mode and we can have the time series of each of them, and of course we can compare the relative importance. So this is not a very good case because I am using a wave which has a frequency exactly in the middle of the frequency of two natural modes. So the actual surface elevation inside the bay is given by a combination of the two natural modes oscillating on their own frequency. So actually on the frequency of the incoming wave. So you can see here from the order of magnitude of the vertical scale that the second and the first longitudinal mode of the bay will oscillate in a similar manner, okay, with a similar amplitude. Okay, this was very well expected. So now let's have a look at the case with a resonant wave. So a wave whose frequency is exactly identical to one of the natural modes. So for example, if we use a frequency of 1.4, what we can see is that the first longitudinal mode that has a natural frequency exactly identical to that of the incoming wave will vibrate a lot. You can see here the vertical scale. This mode is getting energy and energy and energy, while all the other modes, of course, will have a very, very small amplitude, okay? So this is resonance. Not perfect resonance because we have radiation damping. So after some time, the results attain to a stationary value. And okay, I anticipated that this was an academic test because what we obtain is something that we were perfectly expecting. But the good news is that the model, without knowledge about the system, has provided us a very nice decomposition of the contribution of all the modes. And now I am ready to show you instead a very difficult test. Something where we have not a clear idea of what is going on, and it is a test in which solitary waves attack a conical island, okay? And this is a very well-known benchmark for tsunami models that was obtained in laboratory by Briggs and Sinolakis many years ago. And I have, of course, reproduced with the model only a small part of the domain, and I have used a solitary wave identical to that used in the experiments to force the system. And we have, of course, very good, of course, I am happy that we have a very good comparison between the model results and the experiments at some of the positions of the wave gauges used in the experiments. And now I will show you the model decomposition. Okay, so again, it will take a couple of minutes to understand because these are some of the eigenvectors that I have obtained solving the homogeneous version of the equation. And the model has told me that this mode here, this natural mode here, is one of the most important. And I can also have a time series for this mode. And another important mode is this one. And then I have another one. So now let's have a look at the physical meaning of these modes. If we look at the most important one, we see that the surface elevation has a kind of a crest here, a nodal line, a crest, nodal line, crest, and has a shape in the radial direction which tends to decrease exponentially. So this is something which is very similar to an edge wave. And if I calculate the wavelength and I plot the wave number against the frequency, for example, here, I see that it lies perfectly on the frequency dispersion relationship of the zero-order edge wave mode. And very similarly for the second one, it lies on the first-order edge wave mode. So what I can tell from this model, from the results, is that the wave propagation of the solitary wave around the island takes place under the form of edge waves. This is something that was not very easy to say without a very detailed knowledge. And so I am ready now to apply it for very complicated coastal regions, trying to look in details at the contribution of the natural modes of the coast. So these are conclusions. The model is able to simulate the tsunami and attack at the coast and is able of separating the contribution of each natural mode. And so on the basis now of some sample tsunami scenario, I can predict what are the natural modes that are likely to be excited, and what are the places along the coast that are more likely to be inundated. So let me conclude with a very quick invitation to the International Coastal Engineering Conference that I am organizing with Leopoldo Franco in Rome, 2024, September 8 to 14. I will say you something more maybe later in the discussion session. Thank you very much. Thank you.
First of all, thank you for being on time, even too short.
Yeah.
Question. I start with one. Which was the wavelength of the tsunami respect to the diameter of the island?
Well, the solitary wave was had a wave. Okay, the solitary wave has no wavelength, of course, because it is all above the surface, the mean water line. But the order of magnitude of the length was of the same order of the diameter of the island in the experiment.
Same order of the island.
Same order, yes. So, of course, a solitary wave can be seen as the superposition of many frequency and wavelength components, of course. So we can, since I look at the results I can look at the results also in the frequency domain, as in this this plot I am trying to show. I can see how different components of the solitary wave do interact with the coast. Okay, but it was comparable, let's say, in the experiments by Briggs and Sinolakis.
Any further? Or shall we pass to Venice now? Okay, thank you.
Okay, thank you everybody.
Now it is a family affair, because the paper is by Luciana and myself. Luciana will stress one point, but I keep saying we'll talk apparently something completely different, the flooding of Venice, just to be light, towards the end of the meeting. But this is to stress, basically for one target, to stress how important wind waves are also in this case. Luciana, after 15 minutes, of course.
Can you hear? Yes. Okay, thanks again. Everybody's been say thanks, and I'm also glad to be here, to be invited to explain something about our environment. As Gigi was saying, I will explain, try to explain the importance of wave from a different point of view, different than the one we've seen up to now. One of the things that is to understand, Venice is quite, say, close to the sea, and we can have a big flood. And one of the things that happened is 2-3 years ago, that it happened quite a big flood. And to understand why we got, well, that was the situation, I will go back of 1 year, because something similar happened in that case. In that case, we have what was known as the Vaya storm, that is at the European level is called as Adrian in storm. Here is the rather unusual, complicated situation of that day. But I want you to focus on the Adriatic Sea. This is Italy, you know, the Adriatic Sea. Here is the area that has been quite big involved with both storms, the present one and the next one. This arrow indicates the strong wind we have from south east that create a flood, can make flood in the town. We did the study of both the situation of the one of the 2018 and the year after, and we make use of the model we have at our possibility working in the office. One is the meteorological data. We have the data from ECMWF. Then we run in our institute the WOM model with a resolution that is dedicated to the Adriatic Sea. And we have also the Scheiffen model that is evaluating the surge due to the situation, meteorological situation. We also, apart of on top of the model, we also have measurement. Gigi was explaining to some of you, this is the Venice Lagoon. And out of the lagoon, we have this tower that has been there already for almost 60 years. And it's quite a good position because we have a lot of instruments that can be used to validate our model, and also they contribute to the knowledge of the situation in the lagoon. This is what's happened on that day, the 29 and 30 of October. This represents the story of what happened during those 2 days. The thinner line here is showing what is the astronomical tide that we know. Every day we have the tide and is going up and down. But in that occasion, in that days, we also have a surge due to the weather situation. And we have the dotted dashed line is what is being observed, measured, while the blue line was what has been reconstructed by the model. The superposition of the two lines give what is the total sea level. And as Gigi was already mentioning, or we know, we have been lucky in that situation. And lucky why? Because the peak of the situation happened while we had the low tide. If it would have happened 6 hours before, we would have a very worst situation. In fact, here is the reproduction, and Gigi like to play a bit with the data and simulated which would be the situation 6 hours later, or before, sorry, 6 hours in advance. If this surge would have happened 6 hours before, this would have been superimposed to the high tide, and we would have mostly, I'll say 80% of the town submerged by water, because this is 2 meters above the sea level. So in that occasion, we have been lucky. One of the things about that situation, that it was very well forecast. Our institute is connected to the local authority to evaluate the tide and to warn the town about the high tide. And a few days before, we got the phone call. They say, oh, look what is going on, because we have some warning. And in fact, in going to see the ECMWF data, we have here the situation 1 day before, 2 days before, 3 days before, 5 days before. And you see this red spot here is stabling there. Means that some very bad was coming on. As I said about the different model we have running in our institute, one is the WOM model. I have to point out of the discussion we've heard that this model is using ECMWF model, and to have the correct data out of the model, of course, the WOM model is untouchable, as Sasha was saying about the other model. It is physics. What we have to calibrate or to change is the wind. All in all, this is the situation 5 days before the flood that I was presenting before. So this is, you see the wave, this is the story of the wave height, and you have the peak here of about 5 meters. This was 5 days before. Then we go 4, 3, 2, 1. So this was, the situation was very well forecast. In fact, everybody was waiting or closing the doors and around the town. And the situation, as I said, was good enough because here is the time series of the result of the different model. We have the wind, the blue, the black one. Then we have the model. I show you the story before. And we have also the measurement, because we have in the tower, we are measuring also the wind, the wave, tide. And so this is a comparison, and that occasion was, everything went very good. One thing that I have to, because of the importance, as Gigi was saying before, the importance of the wave on the sea level. When we have a wave as the one we had, and is about 5 or 6 meters, one of the things that is happening on the coast, but not many people are considering, is the wave setup. The different line here, the continuous black, is showing what is the measured level at the tower, while this one, the other one, the black one, is the sea level on the Lido, so 15 kilometers far from the tower, and they are different. The blue line here is the enhanced difference between the two lines. So this is essentially the setup. And this is another important thing that we should consider when we evaluate the forecast of flooding in a town. The Vaya storm, I mentioned in the beginning, was a very bad, very nasty situation. In the Dolomite, somebody has been measuring 200 kilometers per hour. And the result was that, to say 20 million trees were flattened. This is one picture. And this is another one. You see all these trees flattened here. And the next one, that was in October. During the winter, of course, the trees were there and left there. Some of them are still there after 3 years. Now, after talking about the storm of 18, we go to the storm of 19. That was also a very special, peculiar event. And in this case, there was a very several situation, and one of those is one of a missed forecast. But we proceed step by step. One of the situations, this is the anomaly of the pressure for that period of November 19. The blue is showing which is the low pressure, so anomaly low pressure over the central Mediterranean, while the red, this is the Atlantic, and this is also the eastern part. This situation make the water of from the Atlantic to enter in the Mediterranean, and make the level of the water rise for about 30 centimeters. The other situation this is rather peculiar of the situation that we have in Venice when we have a flooding, is the low. This is normal for the season of October, November. A low entering, this is the western part of Italy, and producing a wind that we call scirocco, blowing from south, and making a surge and causing the flood of the town. So these two situations, okay, this one, again, these two situations cause a very peculiar general situation at that time. Here we have the mean sea level as has been measured about the end of the 19th century. In the meantime, the sea level rise for several situations, industrial, so normal situation. But on November, this is the line that represented the mean sea level. That is, as I told you before, 30 centimeters higher than usual. We have the tide. The tide is going around this new level. And this is higher. 30 centimeters are what is a normal tide. We have the surge, and we have this is the situation that has been observed, the red line. And this brought up to 1.80 meters of water in the town. So, let's now go step by step. We had one thing, we had low pressure over the Mediterranean, and we had higher level in the water. Then we have a perfect according of phase with the tide. So we have two situations, one on top of the other, but it is not enough. If you look at this map, before I mentioned that this is the general situation with low pressure, but you have to consider also this one. And this is something that was, say, rather unexpected, even if it were forecast. It's something unusual. This is what we can call as a meteorological tsunami. This low has been formed somewhere in southern Italy and run up to the north. And it was forecast because after this event happened, we checked the situation 1, 2, 3, 4 days before. And this line all explain which was the path of this minimum from the south to the north. One of the things that we say missing the wrong forecast is that the last one, this one, pass, if you can see here, pass on the west of Venice. At least was supposed to pass to the west of Venice. This means that this was the forecasted path of the minimum. Instead, it was not like this. Here would have been the wind situation. But if you look at the red arrows, these are the measurement. One are in the tower, the other different location along the coast. And if you look, there is nothing to do, the circulation of the wind, nothing to do with this one. Means that the forecast of this minimum was totally out and was shifted by a few kilometers out. And this was causing something very, very bad. Yes, yeah. In fact, we have the measurement on the tower, and we can start from the pressure. These are the hours. Pressure came down very quickly, and this is because of the path of this, the tsunami. Of course, then accordingly, we have the wind speed. And what is really seriously and is important to remember now is the direction. You see that before it's coming from northeast. Here, because the measurement tower before was coming from northeast. Then after the passage of the minimum was coming from from southwest. And this was really the bad thing that happened for Venice. Really, again, I pass through all this situation because I don't have much time. And as last step, the tremendous wave setup in the lagoon. Again, you have seen this. And we have this situation that rise suddenly. People, a friend that explained, we were unlucky in this sense because we were attending another meeting, not in Venice. And they explained that the wind was blowing from one side, and yes, there was some waves in the lagoon. But what happened is that all this wind make a surge in the southern part of the lagoon. Then suddenly, when the minimum moved, the other side, and we have the change of the wind, all the water that was flowing on the south changed and came in the northern part. And in fact, here, this is interesting. These are tide gauge at the tower. Okay, you cannot maybe read all the number, but you have to consider this one is interesting because this is 1 meter and 87 centimeter in the southern part of Venice. Here is Venice. And if you look at the northern part, you see that the tide is different. There are few, say 20 centimeter difference. And in fact, this was something unexpected by the people and rather unusual. We have a tremendous flow. Oops, no. A tremendous flow of water from the south to the northern part. And so many not canals, but streets were submerged by water. And the water was, due to the wind and the high water, was really very bad. This is a touristic picture taken in those days when this is a San Marco Square. But what is interesting, this is what is one of the Vaporetto many of you may have seen in some television or in Venice, that eventually ended on the river due to the high water level and the strong wind. And waves. These are the damage, the power of waves. And the same here again, destroy the part of this thing. But this is not new. This is something I found. This is of the 17th century. Some painting, the beginning of 17th century. Another one where you see people mostly maybe enjoying the water, but still. All this flood of the 19th century, we, with our colleague connected with the tide, wave, forecasting, we put our effort all together, and we managed in few months before the pandemic to have this published on oceanography. And this is the first page. The picture has been taken on that night. And this is, okay, if you want to. So this is my end. So when will be the next one? For 3 years, we have been quite calm. We'll see. So, but the last, come to Venice before it is too late. And if you have an office for us in case Venice disappears. Okay. Thanks. See. The movie, there is a video. See. The video that you will see has been recorded by the stereo camera. No, these are not a stereo camera, video camera on top of the tower during the first storm. And these are not big enough. The wave you see are 3 meters. And it's still light because the peak was at night, 8 o'clock at night, so everything was dark, we cannot see. We could not record to see. So this was the situation. This is the camera is facing south, so the wave you see are coming from the south as they have been running along the whole Adriatic. And there are quite some, like this one, coming. Quite exciting.
Okay, let me stress one point now. All this look like touristic. It's not. In the first storm, there was a 40 centimeter contribution to the overall flooding due to wave setup. And what I mad about is that my colleague who dealing with the storm surge in Venice do not believe in wave setup. They try to justify everything with wind setup. It is not. In fact, one of the diagrams Luciano showed, the wind was over, but the wave setup was there. It was absolutely coherent with waves. But this was dramatic in the second one, when, as she explained, the low pressure passed above Venice, as the wind changed direction. You had a 120-kilometer wind blowing on something like 30 kilometers of shallow lagoon, 1 meter deep. I don't know if you realize, the wind stress is 1 point, but what was important, you had on 1 meter depth, almost half a meter significant wave height, each single wave breaking. And this is momentum that go in the wind direction, in the wind wave direction. And the key point is that the slope of the mean sea level is inversely proportional to the local depths, which means that practically most of the flood in Venice was due to the wind blowing of the shallow water and the wave setup that was practically pushing water continually against Venice. We gained almost half a meter or 60 centimeters just due to that. And in fact, in the north side of Venice, this was not present, so there was a 30-40 centimeter difference between north and south Venice. So all the canals passing through Venice were like a stream, just a rushing stream, even as a street. We were not there. I'm sorry, as a professional person, not to have been there, because it would have been fantastic, of course. But really, we still have not managed to convince our colleagues that the waves has been the key point of the flooding that night. In fact, this is one of the subjects I want to work on now. So this is a bit entertaining. I find this video fantastic because you really feel the power of waves here, and this is the kind of storm that I've been measuring for about 1 year of my life on board of the tower. I can tell you, it's beautiful. And you learn a lot. And you realize this looks like a big sea. This is only 3 meters significant wave height. And it was 6 meters during the night. So this is the maximum we can have there because it is depth limited. You cannot have significant wave height higher than 40% of the local depths, which means that most of these waves are breaking. And that's why you have waves set up toward the coast, because moving in shallow water, wave breaks, keep breaking, piling up water against the coast, and that is the wave set up. And again, sorry, I've been talking too much. Up to you now, if you want to ask a question. Yeah, up to you. I'm sorry.
Tremendous work. I I like the coastal flooding also. It's my topic also. But I would like to. Well, I have many questions, but I would like to make some related to the beach, because I see the beach also is a very mild slope beach.
Yes, minus slope.
And that induces that the shorter waves dissipates, and the only the infragravity bands lives in the total flooding, the total water level. Yes, but in the top of the wave setup, also you have a swash and oscillation, and that is induced the overtop.
No. We have breaking waves
Mhm.
from the tower toward the coast. The breaking waves are, say, bringing water toward the coast and lifting or rising the sea level. And nothing to do with what you are thinking. Is a different effect.
Okay, Frederick.
Yeah, thank you. So very, very interesting. So in Ireland too, sometimes, we have the combination of the tide and the storm surge, and sometimes we are lucky, sometimes we are not. You mentioned Meteo Tsunami, a small one. So what evidence do you have? Was it observed or?
Well, we noticed, I can tell you, after we came back and started studying the situation, we retrieved all the wind data from ECMWF, the wind field. And I noticed that there was this little structure, not big, but it was forming in the southern, at least it was a combination of the Apennine and the Gargano. So it started there, and then it's been, like, say, transport by the wind along the coast. And it was there, as I told you, 1 day, 2, 3, and 4 days before. No.
What Frederick said, which evidence we have a meteorological tsunami? This was my guess first, because I've seen the velocity of the low pressure along the coast. I estimated the possible advection speed of a tsunami, and it was a coincidence. In fact, the evidence that we should go back, but never mind, is that we have an extremely high tide on the open sea and in the lagoon. In the lagoon, they are due to wave setup. The one on the coast are due to the meteorological tsunami, and we have a 10-20 centimeter exceedance. Of course, we were lucky that the tsunami had no time to enter the lagoon, because he had to enter through the inlet, and actually it was passing, the low pressure was moving very quickly. But yeah, the evidence is given by the tide offshore. Yeah. Well, that's very common in the Adriatic Sea on the Yugoslavian coast, on the Croatian coast. They have some bay that converge and run the system. Okay, thanks. Paolo? Scusa, no, Paolo. Go. Allora, vuoi o no?
Scusami, vedevo lo passavano. Luciana, thank you for this very nice talk. A very quick question. You said that when you have a low pressure on the Mediterranean Sea, of course, the level will rise on the scale of a month, as if I understood correctly. How long the low pressure has to stay there in order so that the water flows from the streaks and actually raise the level in the Mediterranean? Do we have an estimate of that?
But the one I show you was the last 2 or 3 weeks.
2 or 3 weeks.
But normally we have very low tide during the winter, you say January. That is famous, is normal to have a very low tide because we have a high pressure. But that is the high pressure that is the other way around. Sorry.
Okay.
Because the high pressure is pushing the water out of Gibraltar, and the water is not coming in. In some occasion, we have the evaporator that is touching the bottom of the canal. It's happened.
Thank you.
Okay, Luciana, thank you very much. So we move to the last talk. Rúben, are you online?
Hi, Luigi. I'm here.
Okay, good.
Can
we
you hear
cannot
me?
see you.
Can you hear me? Wait a minute. I'm going to share my. Okay. You can see my presentation, Luigi.
Okay.
Wait a minute.
I want to see you.
Hi, Rúben. Turn on your camera.
Anyhow, the title is New
Okay.
Methodology for the
Okay.
Construction Wind Wave Series in Hurricane Condition based on on-site data. Shall we start like this without seeing the speaker or what? I don't know. Okay, Rúben, up
Okay.
to you. Oh, here you are at last. Good.
Hi, Luigi. How are you?
Well, it's quite all right.
Well,
Especially now I see you.
okay.
Carry on.
Thank you. Well, I'm going to start now.
I'll call your
So
attention
first,
after.
I want. Okay. Can you hear
I'll
me?
call
Good.
your attention after 15 minutes, okay?
Okay.
All right,
Well,
go ahead.
okay. First, I want to send some ratings to all the people who is attending this meeting, and I want to send some greetings to our colleagues, Luigi, Ale, Jesus, Nelson, Paco, Eric, to everybody that is attending this meeting. And today I'm going to present just a little part of a big project from an important company, oil company here in Colombia. The name of my presentation is New Methodology for the Construction of Wind and Wave Series in Hurricane Conditions, based on on-site data. The full work was carried out by Mariana Roldán-Peggy from the Medellin University, obviously with the advice from with Andrés Osorio from the National University. So first I'm going to talk about the content of my presentation. I'm going to talk first about motivational background. Secondly, I'm going to talk about the parametric models. In the third place, I'm going to talk about some results. And then I'm going to talk about the most relevant contribution of this research. So as we all of us know, during the hurricane conditions, there are several affectations caused by this kind of phenomenon. So we can mention coastal flooding, coastal erosion, marine ecosystem affectation, infrastructure. So despite the coastal areas of Colombia don't have a high probability to be impacted during this kind of phenomenon, the insular areas of Colombia have a very different situation because are located in a more probably area with be impacted for a hurricane. In the left figure, we can see the flooding occurring during 2020 with the Hurricane Iota in San Andres, Colombia. We are talking about more or less 2 meters deep in some areas of these coastal areas. The water reached more or less 800 meters inside the island, and in the flat areas. Obviously, this affects a lot of people that was located in this area. In the right figure, I want to show the destruction of the infrastructure caused by Hurricane Iota in Providencia. We are talking about 90% of destruction in this island, more than 5,000 people affected for this phenomenon, four people died. So we know that this is a very important topic when we talk about hurricanes, but sometimes you need to try to explain this kind of phenomenon. You need to use a hydrodynamic models, or you have to use wind wave models. But the main question is, what is the best wind data source during hurricane conditions? I like to mention that the word from Luigi, as Luigi said, good winds mean good waves. So, but when you are going to use a wind wave model, you have to select the best option of hurricane winds. But sometimes it's an easy task. We are going to mention some options that we have when we want to obtain. The WRF atmospheric model is a good option, but in our experience, when we compare with other data sources, we think that these kind of models have some disadvantage when compared with other data sets. For example, they require high computational costs. That means sometimes you need to obtain results as fast as possible. For example, for engineering applications, they have complex sensitivity and calibration process. That means that you need expert people that move the parameters inside the model. The parameterization of boundary layer, the microphysics is not easy task. So you need people that have very experience in the atmosphere science. So, they have complex physical parameters. I think that one of the most important is that these models need large quantity of information, and this information sometimes is not available. For example, if you want to model all hurricane, maybe you can obtain the enough information to calculate the boundary condition, the initial conditions, or if you have the information, maybe this have low computational costs, and we are talking about engineering applications. This is very important. If you can use or spend low time in the procedure, you can use this model in any resolution. You can use very high resolution, and they have good ability to obtain long-term analysis and time series. I'm talking that you can obtain good results with few parameters, and you can model all hurricanes that you don't have enough information, or even you can calculate some parameters in a correlation with other few parameters. For example, you can obtain the radius of maximum wind speed as a function of maximum wind speed velocity, latitude, okay, so something like that. And other important thing is that it's possible to consider in these asymmetric models, consider the aspect of asymmetric of the hurricane in nature. Several researchers thought that most of the hurricanes are asymmetric. And I think that these advantages are still really, if we consider that mentioned Jan and Sandra in 2022, that now the new model have become more sophisticated and complex and have yielded better simulation results. So, okay. The main objective of this research was to try to obtain or try to use a specific model and perform our own process of validation, calibration, use our own database, perform our own scripts, perform a long-term analysis. So in this task, we researched the most important asymmetric models. And at the end, we select the model. It showed by Lutich 2005 that corresponds to a generalized Holland model. This model is a modified version of the original version of Holland from the year 1980, but the features included in this new model allow to model with a great accuracy wide range of hurricanes, not only intense hurricanes and narrow hurricanes. You can model too with great accuracy a wide range of hurricanes, large hurricanes, less energetic hurricanes. Another advantage of this kind of model is the inclusion of the Coriolis parameter in the estimation of the shape parameters. some researchers thought that if you don't consider this parameter, you can obtain great errors in the estimation of the maximum wind speed. So we select this model, and the next step was to find what database we can use in the stats. So we work with two data sets. The first of them was the H-wind. This data set is performed by NOAA, and the resolution with this data set is more or less 0.5 degrees, and is in a moving grid with an extension of more or less 9 degrees. The format of this file is shape file, and the information is available since 1993 to 2013. So you have huge information of these hurricanes. This data set it have good accuracy because use a lot of information, use information from aircraft, from the Air Force and NOAA, use information from ship and airport weather reports, use seaman station, platform station, satellites. So it's a lot of information. So it's a data set that it has great accuracy, and even this data set have been using for several researchers for validate his models. The other data set that we employed was the ORDAT2. This data set have information of depth of the hurricane, status. That means if the hurricane the event is tropical depression, tropical storm. It has information for latitude, longitude, maximum sustained wind speeds in knots, minimum pressure in millibars. But the most important information that have this data set for us, for our methodology, is the inclusion of the radius for a specific velocity. The velocities in 4 quadrants, and you can see in this figure. You have information from 34, 50, and 64 knots. So this is very important because with this information in each quadrant, you have information from the asymmetry of the hurricane, and then you have the specific radius, you have the velocity, and you can find the velocity, the maximum velocity around the eye with some methodology. You can perform an iterative process to obtain the radius of maximum wind speed, the shape parameter, the scale parameter, and using these 3 equations. And even you can perform this methodology for any point in the space domain. So with this in mind, the main contribution of our research to solve this problem was to use the information of H-wind and extract more or less 705 rings of wind speed around the hurricane eye. With this information, we discard information in which the hurricanes have the maximum wind speed in the left quadrants, and to discard the information of the hurricanes that have the maximum wind speed that don't reach the category of hurricane according to Saffir-Simpson scale. That means, in conclusion, that we use only the hurricanes that the maximum wind speed was located in the left quadrants, right forward quadrant and right backward quadrant. So in this figure, after this, we obtain more or less 500 rings with information of wind speed around the eye. And with this information, we construct these graphs, as you can see in this figure. The black dots represents all the rings. Remember that we use more or less 500 rings with this information around the hurricane eye, and then we feed this line that represent the average behavior of wind speed around the hurricane eye. The direction is measured in clockwise direction. In that direction, clockwise direction. This was performed for each category. And in the right side of the slide, you can see the equations obtained for describe this behavior or the maximum wind speed around the hurricane eye. The most important of these results is you can obtain the distribution of the maximum wind speed around the hurricane eye. This is the average. And then if you have the information from the real maximum velocity obtained from that data set, you can move this average figure, this average distribution of wind speed around the eye. You can move upwards or downwards based on the real value of the obtained from that data sets. So this is a very important information, because you have information about the variation of the wind speed around the eye. And obviously, this information give information about the asymmetry of the hurricane. So after this process, we perform a blended methodology. The figure in the left represents the results obtained for the proposed model using the distribution of the wind speed around the eye. And in the middle, we have the information of ERA5, the analysis wind speed. And then we perform a blended methodology using both data sets. And the right figure, you can see what is the results of blended these two data sets. The methodology to blended winds was the Montoya et al. 2013. But the most important of the result is that with this kind of model, we obtain a time series of wind and waves during 40 years with all the information on average condition and extreme condition. That means significant with high peak direction, directional spectrum for 40 years of information. Here you can see the domain, mainly is the Caribbean Sea and the Gulf of Mexico. The parameterization that we employed was the old Tolman and Chalikov. The process, obviously, we use analysis, validation, optimization, and then we time this time series of these variables for weight parameters. So I want to show at the end of the presentation some validation of our results. So first, we perform three kind of validation. First, spatial validation. In the figure, in the left of the figure, you can see the winds from the H-wind data set. That is the most accurate data set that all the people use to validate his model. And in the right, you can see the results obtained with our hurricane model, or with the modification proposed. As you can see, the spatial pattern is well reproduced. The velocity around the eye near the hurricane edge is well reproduced. We are talking about more or less 50 meters per second that is observed in both data sets. The spatial pattern, I think that is well reproduced for the space domain. In the bottom, this is another figure. This is the results near the coastal areas of New Orleans. So you can see, when again the model presents very good results of magnitude of wind speeds. There are, well, some difference in the asymmetric behavior of the hurricane, but I think that in the average, the results are very good. So other kind of validation was the estimation of several profiles in several directions, north to south, west to east, among others. This, as you can see in this figure, the red line represents the results obtained with ERA5. That is one of the most accurate data set now. And the blue line and the black line represents the winds measured by H-wind, and the blue line the obtained for our proposal model. And as you can see, for all the hurricanes, the results are very good. But the most important with these results, we think, is that the model reproduces properly the location of the maximum wind speed toward the left or toward the right of the hurricane eye. The better results are obtained for Eager, Dolly, Denise. You can see the model performs very good the reproduction of the full profile along the hurricane. And well, after this, we perform other validation, wind validation, use this buoy located here in the Gulf of Mexico for these hurricanes, Denise, Rita, Katrina, and we compare the results obtained with our model for wind speed and wind direction, where the results are very good in the areas with extreme winds. For Rita, in Katrina, we have some overestimation of wind speed. Ivan, I think that is very good results too. Lily, we see to the wind direction, the model reproduce properly the variability of the wind direction too. So we think that are good results too for the wind speed when we compare with the NOAA voice. And at the end, we perform comparison with significant wave height. We use the WaveWatch 3 model. We perform a comprehensive process of validation, calibration, optimization of the parameters, and then we force the model with our wind speed. So the blue line represents the results obtained with our model. You can see during Emily, but we have to see the results for the most extreme hurricanes. The red line represents the results obtained by ERA5, and the blue line represents the results obtained for our model. As you can see, the results are very good. Agreement with the measurements. Similar results for Katrina. You can see during all the time window, the results are very good with the data measured by the void. During Ivan and Lily during 2002. In the right side of the figure, we can see the peak period that we think that is well reproduced too. So in general, we think that the proposed changes in the selected model are agreed very good with in all kinds of validations, profiles, spatial validation, and even significant wave height or wave parameters. So I'm going to finish with some relevant contributions of this work. We think that we perform new equations to describe the wind speed around the eye, and I think this can increase the quality of the hurricane asymmetry. And this topic is very important because when you model a hurricane, the energy is very different depending on the quadrant of the translation of the hurricane. So if you get some errors in the distribution of energy in the pattern of wind speed of the hurricanes, maybe you are going to get problems too with the ocean waves. We construct a database with 4 years of hurricane wind and wave fields. I think this is a very important information because we can use this information to perform trends analysis. You can perform analyze where there's areas with more activity of hurricanes. We can perform several scientific and engineering applications using this information. And we think that our results can be better than some reanalysis because, as we know, most of the reanalysis don't perform very good during hurricane conditions. So we think that this database that we obtain is have better results than most of the reanalysis during hurricane conditions. And at the end, we think that this information is useful for forecast system because the Hurricane Division Center publish the forecast for 3, 6, and 12 hours in the future, and publish the information, the same information that is published in their data set, their data too. So that means that this methodology can be used for forecast system. So, well, I think that is the end of my presentation. I want to thanks to the event for inviting me. And well, thank you. Gracias.
Thank you, Rúben. I wait for question before asking myself.
Hi, Rubén. How is it going over there? It's Juan here.
Hi. Hello. How are you?
Yeah, very, very well, Rubén. Nice work. I wonder if you are thinking to provide a data article or methods article of your work in order to reproduce your methodology for engineering applications. You know that offshore wind energy is a hot topic in the Caribbean, and it would be interesting applying it.
Well, I don't know if I understand the question, but obviously we want to use this information for kind of applications. So right now we just finished with the research, and now we are working in the paper. But obviously I went to research. We want to use this information in any kind of application, for engineering application, for energy. I don't know. So right now we are trying to finish with the paper, and then in the future we want to share this information from scientific community. Here is Mariana too. My student is here. We have some other specific question from the model.
Yeah, fantastic. Would be nice for selecting areas for the offshore wind plants, offshore wind farms. Will be very interesting how your data could be used for it. Nice. Thank you.
Yeah, great. The idea is we are going to share this information in our website. Right now we are working in our website, and I'm going to put this information in because we want to all the people use this information, test it, and we want to see how are the results when all the people use this information. We are talking about 4 years of data of wind and waves. So I think this is a very useful information.
Rubén, if there is no one else, I will ask a question. First, you allow me a criticism. It's not fair to compare what you call your reanalysis with other reanalysis, because reanalysis like ERA5 with the 31 kilometer resolution, and the practical one is 4 times as much. So that you cannot expect a hurricane reproducibility in those conditions. You should eventually compare with the analysis, of course, of 9-10 kilometer resolution. Second, you mentioned, wait a second, please. Second, you mentioned that your system can be useful for forecast purpose. I don't understand how, because to apply forecast purpose, you need a forecast by someone else. Of course, that they give you the minimum pressure and everything else. So you actually depend on that, because a parametric system can use data of the moment, not to make a forecast. What do you think about?
Yeah, great question, Luigi. So I don't know, maybe I need the help of Mariana, but I understand that the forecasts of the hurricane forecasts publish the same information that is contained in that 2 data sets. So you can have the forecast of the minimum pressure, the 3 points located in each quadrant that give information about the asymmetry of the hurricane. So I think that the forecast give that information, and with that information you can confirm the forecast. But maybe Mariana, you have the full information about this.
Okay.
Well, hello everyone. To attend the question of the Professor Cavalleri, well, the National Hurricane Center of NOAA public the same information of URDAT2 in your hour forecast advisory, public and free, this information is public and free, and is available during the hurricane event at the moment of the hurricane occur. Yes, the National Hurricane Center of NOAA public their advisory with the same information in each quadrant of the hurricane, including to the maximum velocity and the minimum pressure at the moment for 3, 6, and 12 hours.
This information,
yes.
This information that Mariana mentioned is the information during the forecast. The information of these 3 points located in the 4 quadrants is corrected too in the forecast. So you can use this information using this procedure or this methodology, and you can use this information located in the 4 quadrants of the hurricane. So in the forecast, this information is included, and the same information that they got too. So you have this, you use the same information, day, the status, latitude, longitude. You can perform this with a very similar methodology. This is that Mariana is talking about.
All right. Well, Rúben, thanks again.
Okay, thank you, Luigi. Nice to meet you again.
Yeah, sure. Next time in Ecuador in 2 years.
Oh, great.
Okay.
Okay. I invite all of you to come up to the stage, up to the scenery for a photo.
Good afternoon. Hello, can you hear? Yeah. Well, first of all, I would like to thank Rodrigo y la organización de LatWaves that finally we were able to come. 2 years ago, we thought it was going to be impossible, but quien la sigue, la consigue, no? So, I think it's been a very good conference, and I think it's been a very good organized work from Rodrigo and his team. So I really wanted to thank the opportunity to try to present some examples of stuff we do that might have been used in some of the works that have been presented in this conference, and for sure are used in some other works that have not been presented in this conference, but could have been presented in this conference. Okay, I have to do an explanation because for Spanish-speaking people, MASDE is a name that has to do with research and development, because in Spanish, research and development, it's said investigación y desarrollo, and the acronym for that is I+D. So it's not a very bad grade. We are not very bad students in MASDE, which is the first thing that everybody that speaks English says, what, D+? You guys get D+ notes in your exams? It's not that. Maybe some time ago, but the reality is that we try to put tools in the hands of the researchers so they can do their development, the research and development. This is the idea about the MASDE name. Where are we? We are in Madrid, in Spain, and we are inside the university. We are in la Universidad Politécnica de Madrid, in the campus de Montegancedo, which is just outside Madrid. And we decided this place because we have a very, very close relationship with the university and with academia. We foster students that do their master's degree final works or thesis or their degree in engineering thesis with us, and some of them like the stuff we do and stay with us. Some of them just want to run out and go earn real money somewhere else. But we are happy because the relationship between the university and the company is very good and very strong. As a reflection of that, you will see later on that most of our customers are universities around the world. Okay. What do we do? I didn't know if this presentation was going to be in Spanish or in English, so I said I mixed both, and if somebody doesn't understand, I can translate or whatever. But ¿qué hacemos? What do we do? Basically, we like to think of ourselves as inventors, in the sense that we take requirements from researchers that are trying to do something, some experiment, some development, something that they need some tool that might not be on the market. Maybe it's on the market, but they want to have it different. And we come up with an idea that we present in form of a quotation, and if they like it and they have the funds for it, we try to supply this to them, right? So basically, we do the final specification, the design, the fabrication supervision, and the installation of commissioning of whatever tools or toys for our researchers have been agreed upon, okay? Examples. Our first contact with this industry was personally 12 years ago, when in Cantabria, I don't know, many of you, probably all of you know this lab. This lab is in Santander. And for that, we participated in that project, designing the wave maker and the lid for the pit and the walls that can be, the absorbers, the energy absorbers that can be removed, and then they can be carenated with fairings. So we did a whole lot of work that at the end of the day, 2 years later, it became the largest lab in one of the largest labs in Spain. I have a video here for you to see of the wave maker. It's pretty impressive. It's I think it's, if I remember correctly, this is a very old, our first project, let's say it's 24 meters wide and 4.5 meters deep, and it can generate waves up to 2.5 meters in the range of that. So it's pretty massive, pretty impressive. This first unit we produced with a servo hydraulic technology. From that time on, we have evolved a lot, and we are now doing basically servo electric systems. This other basin is quite nice. Here is generating a 3D state on the basin. This is NRCs in Canada, a National Research Council in Canada, Large Area Basin, where we set up a 32-meter front with 64 paddles that can be used to generate 3D states, long crested waves, directional waves, whatever. Okay, I think I skipped one. No, I didn't. Okay. We also do smaller ones. Actually, this is a very nice example. This is the Politécnica School of Madrid, la Universidad Politécnica de Madrid, y la Escuela Técnica Superior de Ingenieros Navales. It's the Naval Architect School in Madrid. Okay, for these guys, we did we took a very old flume and we updated the tow tank carriage with a brand new power plant, a brand new control system, and a wave generator. So now they can do towing tests with waves, and they're quite happy with it. And they are developing all sorts of things, not only ship hulls, but also they're a lot into other elements that must be tested in the ocean, like renewable energy devices, both WECs and foundations for air windmill generators and so forth. This other one is in the University of Hannover, and this is a very nice flume. It's a very old flume. It's Second World War flume. They used to test the submarine missiles in this flume. Now it's not used for that. It's used for other means. And here we implemented a very nice wave generator that can produce this example right here is a 63 centimeter wave with a 4-second period, and it's pretty impressive because we designed this with a very long stroke, so they can do these sorts of waves that you can see. It's hitting the instruments right now. They had some sonar sonic probes, and the wave was too high for what they were trying to read. So that's nice. But this same machine can also do solitons like this one, or solitary waves like this one, which is very nice as well. So this is a smaller one, one for educational purposes. The very nice one about this one is that the paddle is made of carbon fiber, so it's extremely light. And the guidance is of very, very, very high precision. We're talking about 50 microns in precision for the guidance. So we can reproduce with a very, very high precision, very small waves that in some cases, it's interesting. Right there is doing some sort of a Jones Swap spectrum or something like this. This is one of our last babies. This is an IKEA system. I call it an IKEA system because basically we designed it in a way that the customer could build it themselves. And we shipped it with an instructions manual, and they put it up together. And they said, this was pandemic time, so we couldn't do it. We could not go and install it, but they installed them themselves. So we tried to adapt to the situations we get. And then we did all the startup of the system online with them. So it was pretty cool. This is for the University of Sherbrooke in Canada. Besides the machines, the hardware, we also do the controllers and the software. The controller is it's a PLC-based real-time control loop controller. that is very accurate and very fast and very sturdy, very robust. It doesn't matter if it's for one paddle or for 72 or for 57. It doesn't matter. It's the same hardware. We only have to add input-output cards, and it's very scalable. So it's a very good idea, because that way all the development costs go only into one development, and from that point on we can scale the system to whatever needs our customers have. Even if they want to start with one flume, with one paddle, and then they want to move to a basin, they could actually use the same machine, the same controller. They wouldn't have to disconnect it from the flume and connect it to the basin, unless they wanted to run tests simultaneously in both places. And we developed our own software for wave generation, which is it's everyone that has tested it, they think it's very nice, and it's very intuitive, and it has some features that are very interesting. For instance, when you program a Jones-Swamp spectrum with a certain wave height in a certain period, in a certain gamma, before you run the period, the system will give you exactly all the waves that it's going to generate. So you will be checking in the plot where you have the viability of the wave because of the steepness, and the viability of the wave because of the stroke of the machine, and the viability of the wave because of the height of the water height, the water deepness. You will see immediately if some of those waves are outside and they are not going to be produced correctly. So you could decide to eliminate those waves and add equivalent energy, let's say, in terms of waves, before you run your experiment. If you're generating a Jones-Swamp spectrum on the run, you might be generating waves that the machine is not able to make, or the wave is not able to survive the process of generation, let's say. So it's very nice features. If any of you are interested, we can send you a brochure and you could find out more about those. Of course, it generates monochromatic stokes, conoidal waves, solitary waves. It has Pearson-Moscovich, TMA, OCHI, all the famous spectra are there. And it also has an analysis, not only the time series, but also it gives you the energy spectrum, and you can cut off frequencies, you can play with it. It has active absorption, so it's pretty complete. And one thing that we do, since most of our customers are universities, if one of our customers is saying, hey, I really need to use this spectrum, I really need to use this generation method, and it's not implemented, and then we call all of our customers and we give it free for them. It's like once we give them the license, all the updates that come from other people that have had ideas, and we all think it's a good idea, and we were able to implement it correctly, then we give this to everyone so everyone can have it. Changing subjects, we've also worked with wave energy converters. You have to understand that we are mechanical engineers, control engineers. We are guys that 12 years ago, we were not even surfers like some of my colleagues here that know much more about the ocean about me. I know that the ocean is wet, and then if I get into the ocean, I better know how to swim and where I'm getting into the ocean, because I'm exaggerating a little bit. But what I'm trying to say is that we don't pretend to know more than any of you in any of your areas of expertise. We are experts in designing and building systems, machines. We try to learn as much as we can from our users of what they need in order to implement that into the technologies that we develop. But of course, the experts, it's always other people. This means that we not only make wave machines, we work for auto industry, we work for aircraft industry, we work for railroad industry, we work for industries where there is research and development. In the case of wakes and prototype fabrication, we are very good because we have done that for other applications. In the picture there is it's a prototype. No, it's a built sustained suspension arm that is moving on linear motors, and it's part of a wake system that we developed. We've done, this is for Plymouth University. This is going to be installed before the end of the year. And this is a wind generator that is going to go on top of their basin. And they're going to be able to move it with 3 degrees of liberty. They're going to be able to raise it and lower it close to the water level. They're going to be able to translate it across the basin and move it back and forward in the basin. All the motors inside are controllable independently. So they are going to try to generate, and I said, they are going to try to generate profiles in wind because it's not that easy. That is a very complex problem. So they're going to do a lot of experimentation with this system. That looks intentionally, we've made it look a little bit like Star Wars because we are all Star Wars freaks. We're from that generation. So it's really, it's like a wind tunnel. It's not really a wind tunnel, it's a blower. It's a sophisticated blower. And it's going to be moving along the basin with a sort of a crane, let's say, like a rail crane, right? So it's going to be quite interesting. We also do data acquisition systems, miniature data acquisition systems, rugged data acquisition systems, water resistant data acquisition systems and sensors. And we have done some waterproof data acquisition systems, which are not so miniature because we have to work on the protection in order so they don't get soaked and ruined. This guy here is called Grillo because it's a Wi-Fi system. We run we can configure the system by Wi-Fi and we can download all the data by Wi-Fi. That other thing over there is a special load cell, a 16,000 Newton load cell for testing forces in belts and stripes and mooring elements. And this is the last picture. We are now in a mess, let's say. We are in our biggest project. We are building a climatic wind tunnel for Volvo in Sweden, scale 1:1. This is a real Volvo right here. And it's about 275 tons of steel plus motors, actuators. It's going to have snow generation. It's going to have rain generation. It's going to have solar radiation. It's a climatic wind tunnel. The idea is to try to subject the vehicles to real extreme driving conditions, including a dyno under each of the wheels. So if it's a 4-wheel driver, you will have a dyno loading each wheel. And it's so extreme in terms of temperature and environmental conditions because the researchers there are trying to develop the next generation of electric cars and batteries, charging systems, fuel cell technologies are let's say they are sensitive to climatic conditions in terms of efficiency, durability, etc. So this is a huge one. To give you an idea how huge it is, of course, we cannot build this in the Universidad Politécnica de Madrid. We are building this in a shipyard in the north of Spain. And it's not very clear because the picture is not very clear, but these lumps that you see here on the roof, those are people. There's 10 people right there welding in that picture. So, and there the wind tunnel is lying on its belly because it was so big that it didn't fit in the workshop. And we had to lie it on the belly so we can build it completely. And in 2 weeks, it's going to be finished. We're taking it apart and shipping it to Gothenburg, and we will be installing it next year there in Gothenburg. So this is it. This is all the crazy toys we like to design and build. And I'm really grateful to be able to be in an academia environment, because most of our customers come from that environment, and we really learn a lot with each project that we make and with each of the meetings that we attend to. And thank you very much.
Thank you, Enrique. Giorgio, do you want to?
Can you hear me? Yes.
Just a minute.
Okay, giving me the opportunity of presenting this conference and inviting all of you to the international conference in coastal engineering that we are organizing for Rome 2024. And on behalf of the chair of the conference, Professor Leopoldo Franco, I am happy really to invite you, and I'm really looking forward many participants from Latin America. So I will be very quick in this presentation, so that just to give an idea and try to motivate you to come to Rome. And first of all, the venue. The venue is very in the middle of the city. This is a picture taken from the Roman Forum, and just want to show you that the venue is this one. So it is something that it is at a 10 minutes walking distance from the Colosseum. And the idea is that if you have a break in the conference, you want to skip a couple of talks, you can have a very nice nice trip, nice walk around and see the city. So it is a very in the middle of town venue, and it is an old venue, very old-fashioned, with a very big auditorium, able of hosting 1,100 persons. We are expecting something in the order between 800 and 1,100 participants. And about the date of the conference, it will be between Sunday, the 8th of September 2024, and in